When we look up at the night sky, our eyes are drawn to points of light. Stars pierce the darkness. Galaxies shimmer in the depths. We see what shines, what burns, what announces itself across the cosmic void. But between these islands of light, between the spiraling arms of distant galaxies and the glowing cores of stellar nurseries, there exists something we rarely consider, something vast, something that fills nearly all of space. The darkness between the lights is not empty. It is not nothing. It is a universe unto itself, a hidden realm that spans distances so immense that light itself grows weary crossing them. This is the story of that darkness. This is the story of the universe between galaxies. Imagine for a moment that you could step outside our Milky Way. Not just beyond Earth, not just past the Sun, or even past the edge of our solar system, but truly outside our entire galaxy. You would find yourself floating in a space so dark, so profoundly empty of nearby stars, that the concept of darkness itself would take on new meaning. The familiar constellations would be gone. The bright points that guided ancient navigators would have merged into a single cloudy mass behind you. Our entire galaxy, with its 400 billion stars, would appear as a single luminous smudge in your vision, and in every other direction, separated by distances that mock human comprehension, other galaxies would float like distant islands in an infinite sea. This is intergalactic space. This is the between, and it is not empty. The universe is mostly space. This simple statement carries a profound truth that our minds struggle to grasp. When we think of the cosmos, we think of stars and planets, of nebulae and black holes, of all the dramatic structures that populate our astronomical photographs. But these objects, as numerous and vast as they are, occupy an almost infinitesimally small fraction of the total volume of the universe. If you could somehow count all the atoms in all the stars in all the planets, in all the gas clouds and dust lanes within every galaxy we can observe, and then compare that to the volume of space those atoms occupy, you would find that the universe is more empty than the emptiest vacuum we can create on Earth. And yet, calling it empty would be profoundly wrong. Between the galaxies, space stretches in all directions. The distances involved are so vast that even light, traveling at its cosmic speed limit of 300,000 kilometers per second, takes millions or billions of years to cross from one galaxy to another. Our nearest large galactic neighbor, Andromeda, lies 2.5 million light-years away. The light we see from Andromeda tonight began its journey before our human ancestors walked upright on the plains of Africa. That light has been traveling through intergalactic space for all that time, crossing a void that seems to contain nothing at all, but appearances deceive. In that space between our galaxy and Andromeda, in that vast gulf that light takes 2.5 million years to traverse, matter still exists. Not stars, not planets, not anything you could point a telescope at and see with ordinary light, but matter nonetheless, thin beyond imagination, sparse beyond anything we experience in our daily lives. And yet, when you add it all up across the cosmic distances involved, this matter between galaxies contains more mass than all the visible stars and gas clouds within galaxies combined. This hidden mass, this dark presence that fills the spaces between, is one of the great mysteries of modern cosmology. Let us drift deeper into this darkness. Let us leave our galaxy behind and venture into the true depths of intergalactic space, where the distance to the nearest star is measured not in light years, but in millions of light years. Here, in this darkness, the temperature drops to just a few degrees above absolute zero. The cosmic microwave background radiation, the ancient light from the Big Bang itself, bathes everything in its faint glow. This radiation, stretched and cooled by the expansion of the universe over nearly 14 billion years, creates a background temperature of about 2.7 Kelvin. That's roughly minus 270 degrees Celsius. In this cold darkness, matter exists in forms we cannot directly see. The intergalactic medium, as astronomers call it, is composed primarily of hydrogen. This should not surprise us. Hydrogen is the most common element in the universe, forged in the first moments after the Big Bang. But the hydrogen between galaxies exists in a state we rarely encounter elsewhere. It is ionized, stripped of its electron, consisting of bare protons floating in the void. The density of this ionized hydrogen is astonishingly low. In each cubic meter of intergalactic space, you might find just a single hydrogen atom, sometimes fewer. To put this in perspective, the best vacuum we can create in laboratories on Earth contains trillions of atoms per cubic meter. The space between galaxies is a better vacuum than anything we can engineer. And yet, Across the immensity of intergalactic space, these sparse atoms add up. Consider the volume involved. Between here and Andromeda, there are roughly 75,000 trillion cubic meters of space. In that volume, despite the incredible sparsity of matter, there exists a total mass equivalent to millions of solar masses worth of hydrogen. This gas forms a tenuous bridge between galaxies, a connection so thin that we can barely detect it, yet substantial enough to affect the evolution of galaxies themselves. This intergalactic medium is not static. It moves, it flows, it responds to the gravity of galaxies and to the pressure of light and radiation. It is a dynamic component of the cosmic ecosystem, constantly being pulled into galaxies, constantly being ejected from galaxies, constantly cycling between the dense regions where stars form and the vast voids where darkness reigns. But even this thin hydrogen is not the strangest thing in intergalactic space. There is something else out there, something we cannot see at all, something that does not interact with light in any way we can detect, something that reveals itself only through its gravitational effects. We call it dark matter, and it dominates the space between galaxies even more thoroughly than the thin hydrogen gas. Dark matter is one of the great enigmas of modern physics. We know it exists, we can measure its effects, we can map its distribution, but we have never detected a single particle of it directly. We do not know what it is made of. We do not know how it came to exist. We only know that it is there, invisible and intangible, yet more massive than all the ordinary matter in the universe combined. In intergalactic space, dark matter forms vast structures, invisible scaffolding on which galaxies themselves hang like ornaments on a cosmic web. Imagine the universe as a three-dimensional network of filaments. These filaments stretch across hundreds of millions of light years, connecting galaxy clusters and superclusters in a cosmic lattice of stunning complexity. The filaments themselves are composed primarily of dark matter, though they also contain the thin ionized hydrogen of the intergalactic medium. Where filaments intersect, where the density of dark matter grows higher, galaxies congregate. Gravity pulls ordinary matter into these dense nodes, and stars ignite, and galaxies blaze with light. But the filaments themselves, the long tendrils of dark matter that connect these bright nodes, remain dark. They stretch through intergalactic space like highways through wilderness, invisible yet crucial to the structure of everything we see. This cosmic web, as it is called, is perhaps the largest structure in the universe. It extends across billions of light years, encompassing countless galaxies, defining the shape and organization of the entire observable cosmos. And it exists primarily in the space between galaxies, in that darkness we so often ignore. The web was not built by intention or design. It emerged naturally from the physics of the early universe. In the moments after the Big Bang, tiny quantum fluctuations in the density of matter were stretched by cosmic inflation into macroscopic irregularities. Some regions had slightly more matter than others. Over billions of years, gravity amplified these tiny differences. Matter flowed toward the denser regions, pulled by their stronger gravity. The dense regions grew denser. The sparse regions grew emptier. Over cosmic time, this process carved the universe into the web-like structure we observe today. Float with me now through one of these cosmic voids. These voids are the spaces between the filaments, regions where galaxies are rare or absent entirely. They are the true deserts of the cosmos, places where even the sparse intergalactic medium becomes sparser still. A typical void might span 100 million light-years across. Within such a void, you might find only a handful of small galaxies, dim and isolated. The rest is darkness, the rest is empty space, or as close to empty as space ever becomes. In a void, the density of ordinary matter drops to perhaps 1 atom per 10 cubic meters. The density of dark matter is equally low. These regions were bypassed by the cosmic web, left behind as matter flowed along the filaments toward denser regions. Yet even here, even in these voids, the universe is not truly empty. Photons from distant galaxies pass through. Neutrinos stream through in uncountable numbers, barely interacting with anything. The cosmic microwave background bathes everything in its ancient light. Gravitational waves, ripples in the fabric of space-time itself, propagate through the void at the speed of light, carrying information about distant cataclysms, about colliding black holes and merging neutron stars. The void is empty of matter, but it is full of information, full of radiation, full of the invisible fields that permeate all of space. And there is something else in these voids, something even stranger than dark matter, something that pushes outward against gravity, causing the expansion of the universe to accelerate. We call it dark energy, and it is the greatest mystery in all of physics. Unlike dark matter, which clumps and clusters, dark energy appears to be perfectly uniform, spread evenly through all of space. Its effects are negligible on small scales, but across the vast distances of intergalactic space, dark energy dominates. It is causing galaxies to accelerate away from each other. It is causing the universe itself to expand faster and faster, driving galaxies apart, stretching the cosmic web, making the voids larger and emptier with each passing eon. We do not know what dark energy is. The simplest explanation is that it is a property of space itself, a cosmological constant, an energy inherent in the vacuum. Empty space, according to this view, is not truly empty. It has energy. It exerts pressure, and this pressure is negative, causing space itself to expand. But this explanation raises more questions than it answers. If empty space has energy, why does it have the particular value we observe? Why is it not zero or vastly larger? These questions remain unanswered. Dark energy remains a mystery, a fundamental aspect of the universe that we can measure, but not yet understand. As we drift through intergalactic space, contemplating these mysteries, we might wonder what it would be like to truly be here, not observing from Earth, not calculating from equations, but actually present in this darkness. The experience would be unlike anything possible within a galaxy. On Earth, we are surrounded by light. During the day, the sun overwhelms all other sources. At night, the stars provide thousands of points of light, and our own galaxy, the Milky Way, stretches across the sky as a luminous band. Even in the darkest place on Earth, far from cities and under moonless skies, we are surrounded by light sources. But in intergalactic space, the darkness would be nearly absolute. The nearest star would be millions of light years away. Galaxies would be visible, but as faint, distant smudges, fuzzy patches of light against absolute blackness. There would be no sun to warm you, no nearby stars to cast shadows. The cosmic microwave background would be too faint for human eyes to perceive. You would float in a darkness so complete that the human mind, evolved as it is to navigate by light, would struggle to process it. This is not the darkness of a cave or a moonless night. This is cosmic darkness. This is the darkness of true isolation, where the nearest structure of any kind is separated from you by voids that light itself takes millions of years to cross. And yet, you would not be in nothingness. The space around you would be filled with fields. The electromagnetic field, the gravitational field, the quantum fields that underlie all particles and forces. These fields would extend through you and around you, connecting you to the distant galaxies, to the cosmic web, to the entire universe. You would be immersed in the cosmic microwave background, bathed in radiation that has been traveling since the universe was just 380,000 years old. Every cubic centimeter of space around you would contain hundreds of photons from this ancient light, cooled by cosmic expansion but still present, still carrying information about the early universe. The intergalactic medium, thin as it is, would also be present. An occasional hydrogen atom would pass by. Perhaps once every few seconds, a single atom might drift through the volume your body occupies. Over longer timescales, neutrinos would stream through you in vast numbers. These ghostly particles, born in nuclear reactions in stars and in the Big Bang itself, barely interact with ordinary matter. Trillions pass through your body every second on Earth, and you never notice. In intergalactic space, the flux would be lower, but they would still be there, invisible messengers carrying energy across the cosmos. Dark matter would be around you as well, though you would have no way to sense it. Dark matter particles, whatever they are, would be passing through the space you occupy. Their only effect, a tiny gravitational tug. The dark matter density in intergalactic space is higher than the density of ordinary matter, but it is still extraordinarily low by terrestrial standards. And because dark matter does not interact with electromagnetic radiation, does not collide with ordinary matter, its presence would be completely imperceptible to human senses. You could be swimming through a dark matter stream and never know it. Time itself would flow differently here, not in the sense of special or general relativity, though those effects exist as well, but in the sense that the markers of time, the cycles and rhythms we use to measure its passage, would be absent. On Earth, we have days and nights, seasons, the phases of the moon, the movements of the stars. These give structure to time, breaking it into comprehensible units. In intergalactic space, nothing changes. The distant galaxies hang in the void, unchanging on human timescales. There are no days, no seasons, no cycles at all except those measured in millions or billions of years. Time would become abstract, unmeasurable, except by the slow evolution of the universe itself. The expansion of the universe would be happening all around you. Space itself would be stretching, carrying distant galaxies farther away. This expansion is not movement through space. Galaxies are not flying through intergalactic space like rockets. Rather, space itself is expanding, and galaxies are embedded in that space, carried along like raisins in a rising loaf of bread. The expansion is occurring everywhere simultaneously. Here, between galaxies, new space is constantly being created. The void is growing, the distances are increasing, and dark energy is driving this process, pushing the expansion to accelerate. If we could somehow watch this process across billions of years, we would see the cosmic web evolving. Filaments would thin as expansion stretched them. Voids would grow larger. Galaxies within the same cluster would continue to interact, their mutual gravity strong enough to hold them together against the expansion. But more distant galaxies would recede from view, carried away by expanding space. Over truly cosmic timescales, over trillions of years, the expansion will isolate every galaxy cluster. The voids will grow so large that light from distant galaxies will never be able to reach across them. Each cluster will become its own island universe, cut off from all others by an unbridgeable gulf of expanding space. But we are not there yet. Today, the cosmic web still connects the universe. Filaments still channel matter from voids into galaxy clusters. And in these filaments, where the intergalactic medium is densest, complex processes are occurring. The gas in filaments is not completely cold. Though the average temperature of intergalactic space is just a few degrees above absolute zero, the gas in dense filaments can be heated to millions of degrees. This heating occurs through various processes. When gas falls into a filament, pulled by the gravity of the dark matter structure, it accelerates. As it collides with other gas already in the filament, the kinetic energy of motion is converted into heat. This process, called shock heating, can raise the temperature of intergalactic gas to 10 million degrees or more. At such temperatures, the gas emits X-rays. These X-rays are faint, difficult to detect, but they have been observed by space-based telescopes. They reveal the presence of this hot, ionized gas in the cosmic web. The gas glows not with visible light, but with high-energy photons, invisible to human eyes, but detectable by our instruments. This hot gas is part of the baryonic matter that astronomers have been seeking. Baryonic matter is the ordinary matter that makes up stars, planets, and us. It consists of protons, neutrons, and electrons. But when astronomers count all the baryonic matter in stars and in the cold gas clouds within galaxies, they find that a significant fraction is missing. Where is it? The answer lies here, in the intergalactic medium. Much of the missing baryonic matter exists as hot ionized gas in the cosmic filaments. This gas is so hot and so diffuse that it is nearly invisible, detectable only through careful observations of its X-ray emissions, or through the way it affects light passing through it. The cosmic web contains this hidden reservoir of ordinary matter, suspended between galaxies, participating in the slow cycling of matter that characterizes cosmic evolution. This cycling is crucial to understanding how galaxies evolve. Galaxies are not closed systems. They do not evolve in isolation. Instead, they constantly exchange matter with the intergalactic medium. Gas falls from the cosmic web into galaxies, providing fresh material for star formation. Stars form, burn, and eventually die. Some explode as supernovae, ejecting enriched material back into space. This ejected material, enriched with heavy elements forged in stellar cores, flows out of galaxies and into the intergalactic medium. Over time, this enriched gas may fall back into galaxies, either the same ones or different ones, and the cycle continues. This circulation of matter means that the intergalactic medium is not pristine. It is not composed only of the primordial hydrogen and helium from the Big Bang. Mixed in with this primordial material are heavy elements: oxygen, carbon, nitrogen, iron, silicon, magnesium, and all the other elements of the periodic table. These elements were created inside stars, in the nuclear furnaces where hydrogen fuses into helium and helium into carbon, and so on up the periodic table. When massive stars explode, they scatter these elements into space. Some of this enriched material remains within galaxies, but some escapes into intergalactic space, carried by powerful galactic winds or ejected by supermassive black holes. The presence of these heavy elements in intergalactic space tells us that galaxies have been enriching their surroundings for billions of years. The intergalactic medium is a repository of galactic history, a record written in the chemical composition of the gas. By studying this gas, by measuring the abundances of different elements, astronomers can learn about the history of star formation and stellar evolution across cosmic time. But detecting this enriched gas is extraordinarily difficult. The intergalactic medium is so diffuse that even sophisticated instruments struggle to observe it directly. Instead, astronomers use clever indirect methods. One powerful technique involves observing distant quasars. Quasars are extremely luminous objects powered by supermassive black holes in the centers of galaxies. They shine so brightly that they can be seen across billions of light years. When we observe a quasar, the light we receive has traveled through intergalactic space for billions of years. Along the way, it has passed through countless clouds of intergalactic gas. Each cloud leaves its fingerprint on the quasar's light. As light from the quasar passes through a cloud of gas, atoms in the cloud absorb light at specific wavelengths. These absorption features create dark lines in the quasar's spectrum. By studying these absorption lines, astronomers can learn about the properties of the intervening gas. They can determine its composition, its temperature, its density, even its motion. The spectrum of a distant quasar is crisscrossed with hundreds or thousands of these absorption lines, each one representing a different cloud of intergalactic gas encountered along the light's journey. This forest of absorption lines, as it is called, is one of our primary tools for studying the intergalactic medium. The observations reveal a complex picture. The intergalactic medium is not uniform. It is clumpy, structured, varying in density and composition from place to place. Some regions are denser, forming the filaments and sheets of the cosmic web. Other regions are nearly empty, forming the voids. Within the denser regions, gas can collect and cool, eventually becoming dense enough to form new galaxies. This process is ongoing. Even today, new dwarf galaxies are forming in the densest parts of cosmic filaments. Though the rate of galaxy formation is much lower than it was billions of years ago when the universe was younger and denser. The intergalactic medium also contains magnetic fields. These fields are extraordinarily weak by terrestrial standards. The Earth's magnetic field has a strength of about half a Gauss. The magnetic fields in intergalactic space are 1 billion times weaker, with strengths measured in nanogauss or even less. Yet despite their weakness, these fields extend across vast distances. They permeate the cosmic web, threading through filaments and voids alike. The origin of these intergalactic magnetic fields is not entirely clear. They may have been generated by galaxies and then carried into intergalactic space by galactic winds, or they may have emerged from the early universe itself, seeded by processes in the first moments after the Big Bang. These weak magnetic fields can affect the motion of charged particles. Though they exert only tiny forces across the immense distances of intergalactic space, their effects accumulate. High-energy cosmic rays, charged particles accelerated to nearly the speed of light by violent astrophysical processes, can be deflected by intergalactic magnetic fields. This deflection can make it difficult to trace cosmic rays back to their sources. It also means that the intergalactic medium can trap and confine high-energy particles, at least to some degree, creating a dilute population of energetic particles throughout intergalactic space. As we contemplate these phenomena, drifting through our imagined journey in the darkness between galaxies, we might pause to consider the sheer scale of it all. The universe is vast beyond human comprehension. Our Milky Way galaxy contains hundreds of billions of stars, yet it is just one of hundreds of billions of galaxies in the observable universe. The space between these galaxies is not wasted space, not mere emptiness separating the interesting parts. It is a realm in its own right, governed by its own physics, containing its own structures and mysteries. The observable universe extends roughly 46 billion light-years in every direction from Earth. This distance, larger than you might expect for a universe only 13.8 billion years old, is due to the expansion of space. The universe has been expanding throughout its history, and the expansion has been accelerating. Objects that emitted light shortly after the Big Bang have been carried away by expanding space, and are now much farther away than the light travel time would suggest. This means that the volume of the observable universe is immense, containing roughly 2 trillion galaxies by recent estimates. But most of this volume is intergalactic space. If we could add up all the space occupied by galaxies, all the volume contained within their visible boundaries, it would represent less than 1% of the total volume of the observable universe. The rest is between. The rest is the hidden universe we are exploring. This space is where the cosmic web lives. This space is where dark matter and dark energy exert their dominion. This space is the canvas on which the visible universe is painted. In the early universe, things were different. Just after the Big Bang, the universe was hot, dense, and nearly uniform. Matter and radiation were mixed together in a seething plasma. There were no galaxies, no stars, no structures of any kind except tiny quantum fluctuations. As the universe expanded and cooled, these fluctuations grew. Regions that were slightly denser than average attracted more matter through gravity. These overdense regions eventually collapsed to form the first structures. Dark matter collapsed first because it does not interact with radiation and could begin clumping earlier. Ordinary matter fell into the gravitational wells created by dark matter concentrations. Within these wells, the first stars ignited, perhaps just 100 million years after the Big Bang. These first stars were massive and short-lived. They contained no heavy elements, only the hydrogen and helium from the Big Bang. Their nuclear furnaces created the first carbon, oxygen, and heavier elements. When they exploded as supernovae, they scattered these elements into the surrounding space, enriching the intergalactic medium for the first time. Over cosmic time, more and more stars formed, lived, and died. More and more heavy elements were created and dispersed. Galaxies grew larger through mergers and through the accretion of gas from the intergalactic medium. The cosmic web emerged as structure formation proceeded on ever larger scales. Today's universe is the result of nearly 14 billion years of evolution. The structures we see, from dwarf galaxies to superclusters, all grew from those tiny quantum fluctuations in the early universe. The intergalactic medium has been enriched by billions of years of stellar nucleosynthesis. The cosmic web has been carved by billions of years of gravitational collapse and expansion. And the expansion itself has been accelerating for the past several billion years, driven by the mysterious dark energy that dominates the universe's energy budget. Looking toward the future, we can make predictions based on our current understanding. The expansion will continue to accelerate. Galaxy clusters, held together by their own gravity, will remain intact, but clusters will become increasingly isolated from each other. The space between them will grow. Eventually, in hundreds of billions of years, the cosmic web will be stretched so thin that it will effectively disappear. Each galaxy cluster will become a solitary island in an ever-expanding void. The intergalactic medium will become even thinner than it is today, approaching true emptiness. Within each isolated cluster, stars will continue to form for a while, but eventually the gas supply will run out. Stars will age and die. New stars will cease to form. In trillions of years, the last stars will flicker out. The universe will become dark, containing only the faint remnants of once bright galaxies. Black holes will persist, but even they will eventually evaporate through Hawking radiation, a process that takes an unimaginably long time. In the end, the universe will approach a state of maximum entropy, a cold, dark, diffuse sea of particles and radiation, growing ever thinner as space continues to expand forever. But that future is so distant as to be almost abstract. Today, the universe is young. Stars are still being born. Galaxies are still evolving. The intergalactic medium is still being enriched. And we are here to observe it all, to wonder at it, to seek to understand the hidden universe between galaxies. Our journey through intergalactic space brings us to consider one more mystery, the question of what lies beyond. The observable universe is limited by the speed of light and the age of the universe. Light from regions more than 46 billion light-years away has not had time to reach us. But the universe almost certainly extends beyond what we can observe. How far does it go? Is it infinite? Does it have an edge? These questions probe the deepest mysteries of cosmology. Most cosmologists believe the universe is likely infinite, or at least vastly larger than the observable portion. The measurements of the cosmic microwave background suggest that the universe is flat, or very nearly so on large scales. A flat universe with the cosmological constant we observe would extend infinitely in all directions. If this is true, then beyond our observable horizon, there are more galaxies, more cosmic web structures, more voids and filaments, extending forever. The intergalactic medium fills all of this space. The darkness between galaxies is not just a feature of our local universe. It is a universal feature, existing everywhere throughout an infinite cosmos. Alternatively, the universe might be finite but unbounded, with a topology that wraps around on itself. Imagine a three-dimensional version of the surface of a sphere. The surface of a sphere is finite in area but has no edge. You can travel in any direction on a sphere's surface and never reach a boundary. A universe with similar topology would be finite in volume but would have no edge. You could travel in any direction and eventually return to your starting point, like circumnavigating a globe. In such a universe, the intergalactic space would still extend throughout, filling the entire volume, but that volume would be finite. We do not yet know which of these possibilities is correct. Our observations are consistent with a flat, infinite universe, but we cannot rule out alternative topologies. The universe beyond our observable horizon remains forever beyond our direct knowledge. We can theorize, we can extrapolate from what we see, but we cannot observe it. This is a fundamental limitation imposed by the finite speed of light and the finite age of the universe, and yet, even this limitation is itself profound. It means that each observer in the universe occupies the center of their own observable universe. An observer in a galaxy billions of light years from us would see a different portion of the cosmos. Their observable universe would overlap with ours, but would also include regions we can never see. In this sense, there are countless observable universes, one for each possible observer, each one 46 billion light years in radius, each one centered on a different point in space. The true universe contains all of these overlapping observable universes and extends beyond them all. In the darkness between galaxies, this insight takes on a particular poignancy. Here, far from any particular galaxy, you could look in all directions and see distant islands of light, each one a galaxy or cluster of galaxies, each one separated from you by immense voids. From your vantage point, the universe would appear much as it appears from Earth, a vast distribution of galaxies stretching to the limits of vision. An observer in any of those distant galaxies would see something similar. From their perspective, they would be in the center, and our galaxy would be a distant speck. The universe has no privileged center. Every location is equivalent, at least on large scales. This is the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales, and observations confirm it. Intergalactic space embodies this principle. The properties of the intergalactic medium are similar everywhere. The density varies from filaments to voids, but the average density is the same throughout the universe. The cosmic microwave background has the same temperature in all directions, aside from tiny fluctuations. Dark matter is distributed similarly everywhere, forming web-like structures throughout the cosmos. Dark energy is even more uniform, showing no variation at all as far as we can measure. The laws of physics are the same throughout intergalactic space. Gravity operates the same way here as it does on Earth. Light travels at the same speed. Particles have the same properties. The universe, for all its vastness, is governed by universal laws. This universality is what allows us to study intergalactic space from our location in the Milky Way. We do not need to travel to those distant voids to understand them. We can observe the light that passes through them. We can study the cosmic microwave background, which carries information about the universe as a whole. We can simulate the formation and evolution of the cosmic web using powerful computers, applying the laws of physics we have learned on Earth and in our local cosmic neighborhood. These simulations reproduce the observed large-scale structure of the universe remarkably well, giving us confidence that we understand the basic physics at work. The simulations start with the conditions of the early universe. Just after the Big Bang, they model the expansion of space, the cooling of matter and radiation, the growth of structure from initial quantum fluctuations. They include dark matter, ordinary matter, and dark energy, each following its own physics. As the simulation runs forward in time, structures emerge. Dark matter clumps into halos. Ordinary matter falls into these halos and cools. Stars form. Galaxies assemble. The cosmic web takes shape. After billions of years of simulated evolution, the result looks strikingly like the real universe we observe. These simulations reveal details that are difficult to observe directly. They show how gas flows along filaments from voids into galaxies. They show how galaxies merge and evolve over cosmic time. They show how the intergalactic medium is heated by shocks, and enriched by galactic outflows. They provide a theoretical framework for understanding the observations, connecting what we see to the underlying physics. Without these simulations, the complexity of cosmic structure formation would be nearly impossible to unravel. Yet simulations have their limitations. They require assumptions about the nature of dark matter and dark energy, entities we do not fully understand. They must approximate certain physical processes that occur on scales too small to simulate directly. They cannot yet include all the complex feedback mechanisms that regulate galaxy formation. Despite these limitations, simulations have become an indispensable tool in cosmology, allowing us to test theories, make predictions, and interpret observations. As we continue our drift through intergalactic space, we might contemplate what it would mean to truly explore this realm. Human space travel is currently limited to our own solar system. The nearest star, Proxima Centauri, is over 4 light-years away, an immense distance by current technological standards. Traveling to another galaxy is beyond even speculative technology. Andromeda, our nearest large neighbor, is 2.5 million light-years distant. At current spacecraft velocities, reaching Andromeda would take tens of billions of years, longer than the current age of the universe. Even if we could somehow travel at the speed of light, which physics tells us is impossible for objects with mass, the journey would take millions or billions of years. And upon arrival, we would find that the galaxy we were traveling to had moved during our journey. The expansion of space would have carried it farther away. For the most distant galaxies, those near the edge of the observable universe, the situation is even more extreme. These galaxies are receding from us faster than the speed of light, not because they are moving through space at such speeds, but because the space between us and them is expanding. Light emitted from these galaxies toward us will never reach us if it is emitted after a certain point in cosmic time. These galaxies are passing beyond what is called our cosmological event horizon, leaving the observable universe from our perspective. This means that much of intergalactic space is not just currently unreachable, but will forever remain unreachable. We will never be able to travel there, never be able to send a probe there, never be able to receive information from there. The accelerating expansion driven by dark energy is creating a boundary, not in space, but in time and causality. The universe is not just vast, it is becoming more isolated. Future civilizations, if any arise billions of years hence, will observe a very different universe than we do. They will see far fewer galaxies. Most of the galaxies we see today will have been carried beyond their cosmological horizon. They will infer a smaller, emptier universe, one consisting perhaps of just their local galaxy cluster, surrounded by darkness in all directions. But we live now in an era when the universe is still rich with observable structures. We can see the cosmic web, we can detect the intergalactic medium, we can observe distant galaxies and study their properties. We are privileged to live in a time when the universe reveals its full glory, before dark energy has erased most of it from view. This realization lends a certain urgency to cosmological research. The universe will not always be as observable as it is today. Every generation of astronomers has a limited window in cosmic time, during which certain observations are possible. The darkness between galaxies, in this light, becomes not just a physical realm, but a temporal one. It is a space defined by distance, yes, but also by time, by causality, by the expanding fabric of space-time itself. To understand intergalactic space is to understand the very nature of the cosmos, its past, present, and future. It is to grapple with questions that transcend mere measurement and calculation, questions that touch on the fundamental nature of existence itself. As we float in this imagined darkness, surrounded by the faint glow of distant galaxies, we might begin to appreciate the philosophical dimensions of intergalactic space. This emptiness is not a void in the nihilistic sense. It is not absence. It is presence of a different kind. It is the medium through which causality propagates. It is the stage on which cosmic evolution unfolds. It is the container that holds all structure, all matter, all light. Without this space, without this darkness between galaxies, the concept of separation would have no meaning. There would be no distance, no isolation, no individual structures. Everything would collapse into a single point. The darkness preserves distinction. It allows galaxies to be separate entities, each with its own history, its own collection of stars and planets, its own potential for complexity, and perhaps even life. The intergalactic voids are not barriers but boundaries, defining where one system ends and another begins. They create the conditions for diversity, for the rich variety of structures we observe throughout the cosmos. In a universe without this darkness, without these vast separations, homogeneity would reign. The darkness enables heterogeneity. Consider the silence of intergalactic space. Sound, as we experience it, requires a medium. It is a pressure wave traveling through air or water or some other material. In the near vacuum of intergalactic space, sound cannot exist. There is no medium dense enough to carry pressure waves. The universe here is silent in a way that is absolute. No vibration disturbs the sparse atoms. No acoustic wave propagates through the void. This silence is deeper than any silence we can experience on Earth. Even in the quietest places, in soundproofed rooms or deep underground chambers, there are still air molecules vibrating. Still the subtle sounds of our own bodies, our heartbeat, our breathing, the rush of blood through our veins. But in intergalactic space, there would be nothing. Perfect silence. The silence of the tomb multiplied by infinity. Yet this silence is misleading in its own way. Intergalactic space is full of information. Electromagnetic waves of all frequencies pass through it constantly. Radio waves from distant galaxies and quasars. Microwaves from the cosmic background. Infrared radiation from warm dust. Visible light from stars. Ultraviolet and X-rays from hot gas and violent processes. Gamma rays from the most energetic events in the universe. All of these electromagnetic messengers travel through intergalactic space at the speed of light, carrying information across cosmic distances. If we could translate this electromagnetic activity into sound, the universe would be deafeningly loud, a cacophony of signals from countless sources overlapping and interfering with each other. Gravitational waves add another layer to this cosmic symphony. These ripples in space-time propagate through the universe at light speed, passing through matter and electromagnetic fields alike. They carry information about the most violent events, about colliding black holes and neutron stars, about the vibrations of supermassive black holes in galactic centers, perhaps even about the Big Bang itself. The Laser Interferometer, Gravitational Wave Observatory, LIGO, and similar detectors on Earth have begun to listen to this gravitational music. Each detection reveals another event from the distant past. Another cataclysm that occurred millions or billions of years ago and whose gravitational echo has finally reached us, having traveled through all the intergalactic space between. Neutrinos provide yet another channel of information. These nearly massless particles are produced in vast numbers by nuclear reactions in stars, by supernovae, by the interactions of cosmic rays with gas, and by other high-energy processes. They travel at nearly the speed of light and interact so weakly with matter that they can pass through entire planets without stopping. Neutrinos from the Sun reach Earth in about 8 minutes, the same time it takes light to make the journey. But neutrinos from distant galaxies, having traveled through billions of light-years of intergalactic space, also reach us, carrying information about conditions in those faraway regions. Neutrino astronomy is still in its infancy, but it promises to reveal aspects of the universe invisible to other forms of observation. All of these messengers, photons and neutrinos and gravitational waves, traverse intergalactic space freely. The darkness does not impede them. The emptiness does not block them. They travel in straight lines, or as straight as the curved geometry of space-time allows, from their sources to our detectors. This transparency of intergalactic space to radiation is what makes astronomy possible. If the space between galaxies were opaque, if it absorbed or scattered electromagnetic radiation, we would see only our local neighborhood. The distant universe would be hidden from us. But intergalactic space is transparent, at least to most wavelengths, allowing us to observe across billions of light years. There are some exceptions to this transparency. The intergalactic medium can absorb certain wavelengths of light. Ultraviolet light, for example, is strongly absorbed by neutral hydrogen. This is why distant quasars show strong absorption at ultraviolet wavelengths that have been redshifted into the visible range by cosmic expansion. The absorption tells us about the distribution and properties of hydrogen gas along the line of sight. But for most wavelengths, intergalactic space is remarkably transparent, a clear window through which we can observe the distant universe. This transparency has profound implications. It means that when we look at distant galaxies, we are seeing them as they were billions of years ago. The light we receive from a galaxy 10 billion light-years away was emitted 10 billion years ago, when the universe was less than a quarter of its current age. We are literally looking back in time. Astronomy is the only science where time travel, in this limited sense, is not just possible, but unavoidable. Every observation of a distant object is an observation of the past. The farther we look, the farther back in time we see. The deepest images taken by telescopes like Hubble and James Webb show galaxies as they appeared more than 13 billion years ago, less than a billion years after the Big Bang. These galaxies look different from nearby galaxies. They are smaller, more irregular, more actively forming stars. We are witnessing the early stages of galaxy formation, seeing the universe as it was in its youth. The light from these galaxies has traveled through intergalactic space for more than 13 billion years, crossing an immense gulf of space that has been expanding all that time. The galaxies themselves are now much farther away than 13 billion light-years, carried by expanding space to distances of 30 billion light-years or more. Intergalactic space acts as a time machine, preserving the light from the distant past and delivering it to us in the present. The darkness between galaxies is a historical archive, containing information about every era of cosmic history. Light emitted at different times, from different distances, reaches us continuously, providing a layered view of cosmic evolution. By observing galaxies at different distances, astronomers can trace the history of star formation, the assembly of galactic structure, the evolution of the intergalactic medium, and the changing influence of dark energy. This historical archive extends to the cosmic microwave background itself. This radiation, the oldest light in the universe, has been traveling through intergalactic space for nearly 14 billion years. It was emitted when the universe was just 380,000 years old, at the moment when the cooling plasma of the early universe became transparent to radiation. Before this moment, photons were constantly scattered by free electrons, and light could not travel far. After this moment, called recombination, electrons combined with protons to form neutral hydrogen atoms, and photons were free to stream through space unimpeded. The cosmic microwave background is the light from this moment, stretched by cosmic expansion from visible and infrared wavelengths into microwaves. The tiny temperature fluctuations in the cosmic microwave background map tell us about the density fluctuations in the early universe, the seeds from which all structure grew. These fluctuations are imprinted on the radiation and have been carried through intergalactic space to us, a message from the beginning of time. By studying this radiation, cosmologists can determine fundamental properties of the universe: its age, its composition, its geometry, its expansion history. The cosmic microwave background is the most distant thing we can directly observe, and it has traveled through more intergalactic space than anything else we see. In contemplating these vast distances and times, we confront one of the most humbling realizations in all of science. The universe does not care about human timescales or human distances. The processes that govern intergalactic space operate over billions of years and billions of light years. Stars are born and die. Galaxies collide and merge. The cosmic web evolves. Dark energy drives acceleration. All of this happens on timescales that dwarf human history. Our entire civilization, from the first agricultural settlements to the present day, spans perhaps 10,000 years. The universe is more than 1,000,000 times older. The light we see from distant galaxies began its journey before Earth even existed. This cosmic perspective can be disorienting. It challenges our sense of significance. In the vastness of intergalactic space, Earth is less than a mote of dust. Our Sun is one of hundreds of billions of stars in our galaxy, which is one of hundreds of billions of galaxies in the observable universe. The total number of stars in the observable universe is estimated to be around 10 to the 24th power, a 1 followed by 24 zeros. That is more stars than all the grains of sand on all the beaches of Earth. And between all those stars, between all those galaxies, lies the darkness, the intergalactic medium, the cosmic web, the hidden universe that occupies most of space. Yet within this vastness, complexity arises. On at least one planet orbiting one star in one galaxy, life emerged. Simple at first, but growing more complex over billions of years. Eventually, beings capable of thought, of language, of science arose. We are those beings. We have developed the capacity to observe the universe, to measure it, to understand it. We can look out across intergalactic space and comprehend what we see. We can infer the existence of dark matter and dark energy. We can trace the history of the cosmos from the Big Bang to the present. We can predict its future evolution. This capacity for understanding is itself remarkable, a phenomenon that seems to be rare in the universe, or at least rare enough that we have found no definitive evidence of it elsewhere. The question of whether life exists elsewhere in the universe is intimately connected to the nature of intergalactic space. Life as we know it requires certain conditions. It needs a source of energy, usually a star. It needs complex chemistry, which requires heavy elements beyond hydrogen and helium. These heavy elements are created in stars and dispersed into space by supernovae and other processes. They mix into the interstellar medium within galaxies and are incorporated into new generations of stars and planets. But these heavy elements also escape into intergalactic space, carried by galactic winds and outflows. The intergalactic medium, as we have discussed, contains heavy elements, evidence of billions of years of stellar nucleosynthesis and galactic enrichment. Could life exist in intergalactic space itself? Almost certainly not. The densities are far too low. The temperatures are too extreme, either extremely cold or extremely hot in the case of gas in cosmic filaments. There are no energy sources, no stable platforms on which complexity could arise. Life requires a concentrated source of matter and energy, conditions found in planetary systems around stars, not in the vast emptiness between galaxies. But life that arises in galaxies is connected to intergalactic space through the cycling of matter. The atoms that make up living beings were created in stars, and some of those atoms may have spent time in intergalactic space before being incorporated into the molecular clouds that formed our solar system. In a very real sense, we are made of stardust, as Carl Sagan famously noted. But we are also connected to the intergalactic medium, to the cosmic web, to the entire universe through the history written in our atoms. The hydrogen in water molecules in our bodies was created in the Big Bang. The carbon in our cells was forged in the cores of stars. The oxygen we breathe was created in massive stars and scattered into space by supernovae. These atoms have journeyed through space and time, perhaps passing through intergalactic space at some point in their history, before finally coming together on Earth to form the complex molecules of life. This connection makes intergalactic space less remote, less alien. It is not separate from us. It is part of the same universe that created us. The same laws of physics that govern the motion of gas in cosmic filaments also govern the chemistry of life. The same force of gravity that pulls galaxies together also holds us to the surface of Earth. We are not outside observers looking at the universe from some privileged position. We are inside the universe, part of it, made from it, governed by its laws. Our ability to understand intergalactic space is the universe understanding itself. This recursive insight has been articulated in various ways by scientists and philosophers. The universe has given rise to complexity, and that complexity has given rise to consciousness, and that consciousness has developed the ability to observe and comprehend the universe. We are a means by which the cosmos comes to know itself. In studying intergalactic space, in mapping the cosmic web, in searching for dark matter and dark energy, we are engaging in a profound act of cosmic self-discovery. The darkness between galaxies, then, is not just a physical space but a conceptual space, a place where profound questions intersect. Questions about the nature of space and time, questions about the composition and fate of the universe, questions about the origins of structure and complexity, questions about our own place in the cosmic scheme. These questions do not have easy answers. Many remain open, subjects of ongoing research and debate. But the questions themselves are part of what makes us human, part of what drives us to explore and understand. In the silent darkness of intergalactic space, these questions resonate with particular clarity. Stripped of the familiar landmarks of daily life, freed from the constraints of earthbound thinking, we can contemplate the universe in its full grandeur. The distances that separate galaxies are not obstacles but invitations, calling us to expand our understanding, to push the boundaries of knowledge ever outward. The darkness is not a limit, but a frontier, an unknown realm waiting to be explored, if not physically, then intellectually. Modern cosmology has made tremendous progress in understanding intergalactic space. We have mapped the large-scale structure of the universe. We have measured the properties of the intergalactic medium. We have detected dark matter through its gravitational effects. We have discovered dark energy and measured its influence on cosmic expansion. We have observed the cosmic microwave background and extracted from it a wealth of information about the early universe. These achievements represent some of the greatest triumphs of human intellect, products of centuries of observation, theory, and technological innovation. Yet much remains unknown. The nature of dark matter is still a mystery. Physicists have proposed many candidates, from weakly interacting massive particles to axions to primordial black holes, but none have been definitively detected. The nature of dark energy is even more mysterious. Is it truly a cosmological constant, an energy of the vacuum itself, or is it something more exotic, a new field or force that we have not yet identified? These questions cannot be answered by studying galaxies alone. The answers lie in intergalactic space, where dark matter and dark energy dominate. The search for dark matter particles continues in laboratories around the world. Detectors deep underground wait for the rare collision of a dark matter particle with ordinary matter. Other experiments search for the signals that would indicate dark matter particles annihilating or decaying. Still others look for axions, hypothetical particles that would convert to photons in the presence of strong magnetic fields. So far, these searches have not found conclusive evidence. The dark matter, if it consists of particles, is more elusive than we hoped, but the search continues, driven by the conviction that understanding dark matter is essential to understanding the universe. Dark energy presents even greater challenges. Unlike dark matter, which clumps and can be mapped through its gravitational effects on visible matter, dark energy appears to be perfectly uniform. Its effects are apparent only on the largest scales in the acceleration of cosmic expansion. Measuring this acceleration requires observing very distant galaxies and determining their distances and velocities with high precision. Supernova observations, measurements of the cosmic microwave background, and studies of large-scale structure all provide evidence for dark energy. These independent lines of evidence agree, giving us confidence that the acceleration is real. But explaining the acceleration, deriving it from fundamental physics, remains an unsolved problem. Some physicists have proposed modifications to general relativity that might explain the observed acceleration without invoking dark energy. Others suggest that our observations might be misleading, that we might live in an unusual region of the universe that gives a false impression of universal acceleration. Most cosmologists, however, accept dark energy as real and seek to understand its properties. Is it constant over time, or does it evolve? Does it have any structure, any variation from place to place? These questions require increasingly precise observations of the distant universe, observations that probe deep into intergalactic space. The answers to these questions will shape our understanding of the universe's fate. If dark energy is a cosmological constant, unchanging over time, then the universe will continue to expand at an accelerating rate forever. Galaxies will become more isolated. The cosmic web will stretch and thin. Eventually, in the far future, the universe will approach a state of maximum entropy, cold and dark and nearly empty. This scenario, sometimes called the Big Freeze or heat death, is the current best estimate of the universe's ultimate fate based on our observations. But if dark energy is not constant, if it changes over time, then other futures are possible. If dark energy weakens in the future, the expansion might slow down, perhaps even reversing into a contraction that would lead to a big crunch, where the universe collapses back into a hot, dense state. If dark energy strengthens dramatically, it could lead to a big rip, where the accelerating expansion becomes so strong that it tears apart galaxies, stars, planets, atoms, and eventually space-time itself. These scenarios are speculative, but they illustrate how much depends on understanding the properties of dark energy. Intergalactic space is where the fate of the universe will be decided. The darkness between galaxies is where dark energy exerts its influence. The voids are where expansion is most apparent. By studying these regions, by measuring the rate of expansion at different cosmic epochs, astronomers can constrain the properties of dark energy and narrow down the possible futures. This research connects the smallest scales of particle physics to the largest scales of cosmology, bridging the quantum and the cosmic in a quest to understand the fundamental nature of reality. As we continue our meditation on intergalactic space, drifting through this imagined darkness, we might reflect on the tools that allow us to explore this realm. Telescopes are our eyes, extending our vision across the electromagnetic spectrum. Radio telescopes detect the longest wavelengths, revealing cool gas and the synchrotron radiation from energetic particles in magnetic fields. Infrared telescopes pierce through dust and observe the cool universe, the dimly glowing stars and galaxies too faint for visible light. Optical telescopes capture the light our eyes can see, though with far greater sensitivity and range. Ultraviolet, X-ray, and gamma-ray telescopes observe the hot, violent, energetic universe, regions where matter is heated to millions of degrees or where particles are accelerated to near-light speeds. Each wavelength provides a different view of intergalactic space. Radio waves reveal the structure of magnetic fields and the distribution of cosmic rays. Infrared light shows us distant, dusty galaxies and the cool intergalactic medium. Visible light traces the stars and galaxies themselves. Ultraviolet observations probe the hot gas in galaxy halos and the ionized intergalactic medium. X-rays map the hot gas in cosmic filaments and galaxy clusters. Gamma rays indicate the most extreme processes, the acceleration of particles to the highest energies observed in nature. Together, these observations across the electromagnetic spectrum build a comprehensive picture of intergalactic space. No single wavelength tells the whole story. Each reveals different components, different processes, different aspects of the physics at work. This multi-wavelength approach has become standard in modern astronomy, recognizing that the universe emits radiation across the full spectrum and that understanding it requires observing across that spectrum. Beyond electromagnetic radiation, other messengers provide additional information. Neutrino detectors, located deep underground or deep in ice, capture the occasional neutrino interaction and trace these ghostly particles back to their cosmic sources. Gravitational wave detectors measure the minute distortions of space-time caused by passing gravitational waves, opening an entirely new window on the universe. Cosmic ray detectors measure the high-energy particles that arrive at Earth from space, seeking to understand their origins and the processes that accelerate them. Each of these observational techniques has its challenges. Space is a hostile environment for instruments. Telescopes in orbit must be carefully designed and shielded to survive the radiation environment. They must be precisely pointed and stabilized to observe faint, distant objects. Ground-based telescopes must contend with Earth's atmosphere, which distorts and absorbs much of the incoming light. Adaptive optics systems and high-altitude sites help mitigate these effects. But space-based observation remains the gold standard for many applications. The James Webb Space Telescope, launched in late 2021, represents the current pinnacle of infrared space astronomy. Its large mirror and sensitive instruments allow it to observe the most distant galaxies ever seen, looking back to the first billion years after the Big Bang. Webb can study the intergalactic medium by observing how it absorbs light from background sources. It can examine the chemical composition of gas in and around galaxies. It can trace the flow of matter through cosmic filaments. These observations will refine our understanding of how the universe evolved from its smooth, early state to the structured cosmos we see today. Future missions will push even further. Concepts for even larger space telescopes are being developed. New technologies for detecting gravitational waves and neutrinos will increase sensitivity and expand the range of observable sources. Advances in computing will enable more sophisticated simulations, capable of modeling the universe with ever greater fidelity. The study of intergalactic space will continue to advance, driven by new observations, new theories, and new questions. But amid all this technological progress, the fundamental mystery remains. Why does the universe exist at all? Why is there something rather than nothing? These questions take us beyond physics into metaphysics, beyond science into philosophy. The darkness of intergalactic space offers no answers. It simply exists, vast and silent, indifferent to our questions. Yet the very fact that we can ask such questions, that we can observe and measure and comprehend this darkness, suggests that the universe has a strange property. It is comprehensible. The laws of physics are mathematical, elegant, amenable to human understanding. This comprehensibility is itself mysterious. Why should the universe be knowable? Some physicists and philosophers have argued that the universe must be comprehensible, because otherwise we would not exist to observe it. This anthropic reasoning suggests that the properties of the universe are, in some sense, selected by the requirement that they allow for the existence of observers. If the laws of physics were very different, if the fundamental constants had different values, perhaps stars would not form, or chemistry would not work, or complexity would never arise. We observe this particular universe with its particular laws and constants because this is a universe that allows for our existence. This line of reasoning is controversial. Some find it profound, a deep insight into the nature of reality. Others find it circular, an explanation that explains nothing. The debate continues, unlikely to be resolved soon. But the question it addresses is real and significant. The universe does seem to be fine-tuned for complexity, for the existence of stars and galaxies, and ultimately, for life. Change certain fundamental constants by even small amounts, and the universe would be sterile, devoid of structure, unable to support complexity. Intergalactic space participates in this fine-tuning. The density of dark matter, the strength of dark energy, the initial conditions after the Big Bang, all had to fall within narrow ranges for the cosmic web to form as it did. If dark matter were much denser, it would have collapsed into black holes early in cosmic history, preventing galaxy formation. If it were much less dense, galaxies would never have formed at all. If dark energy were much stronger, it would have torn apart structures before they could form. If it were weaker, the universe might have recollapsed before stars could evolve and die and create heavy elements. The balance is delicate. The universe teeters on a knife edge between collapse and dispersion, between homogeneity and fragmentation. Intergalactic space exists in its current form because of this balance. The darkness between galaxies is neither absolute emptiness nor dense fullness. It is a middle ground, a regime where gravity and expansion, dark matter and dark energy reach a dynamic equilibrium that allows for the structures we observe. In this equilibrium, we find beauty. The cosmic web, with its filaments and voids, its clusters and superclusters, exhibits patterns that are aesthetically striking. When cosmologists create visualizations of large-scale structure, the results resemble abstract art. Delicate threads of light trace cosmic filaments. Dark patches indicate voids. Bright nodes mark galaxy clusters. The overall pattern is organic, reminiscent of neural networks or the structure of biological tissues. This resemblance is not coincidental. The same mathematical principles that govern pattern formation in many contexts, from physics to biology to mathematics itself, are at work in shaping the cosmic web. Gravity amplifies density fluctuations, creating a feedback loop where dense regions grow denser and pull in more matter. This process, operating across cosmic scales, generates hierarchical structures. Small structures form first, then merge to form larger ones. Galaxies form from smaller proto-galaxies. Clusters form from merging groups. Superclusters represent the largest collapsed structures. This hierarchical clustering is a prediction of gravitational structure formation, and observations confirm it. The universe is organized in a hierarchy of structures, each level emerging from the interactions of smaller components. Intergalactic space is the medium through which this hierarchy is expressed. The voids separate clusters. The filaments connect them. The sheets define planes along which structures align. This cosmic architecture is not random, but ordered, shaped by the laws of physics, acting on the initial conditions of the universe. And those initial conditions, encoded in the fluctuations of the cosmic microwave background, were themselves products of quantum processes in the very early universe, perhaps during an inflationary epoch just after the Big Bang. Inflation is a theoretical period of exponential expansion that occurred in the first fraction of a second after the Big Bang. During inflation, quantum fluctuations in fields were stretched to cosmic scales, providing the seeds for all later structure. These fluctuations were tiny, just parts per 100,000 in density, but they were enough. Over billions of years, gravity amplified them into galaxies and clusters and the cosmic web. Inflation explains why the universe is so uniform on large scales, yet has just enough fluctuation to form structure. It explains the flatness of the universe, the lack of exotic relics from the Big Bang, and other features that would otherwise be mysterious. If inflation occurred, then the observable universe is just a tiny patch of a much larger, perhaps infinite, inflated region. Beyond our cosmological horizon, space continues, containing more structure, more cosmic webs, more galaxies. These regions are forever beyond our observation, their light unable to reach us because of the expansion of space. In this picture, intergalactic space extends not just across the observable universe, but far beyond, into regions we will never see, governed by the same laws, but with different specific configurations of matter. Some versions of inflation suggest that different patches of the inflated universe might have different properties, different values of physical constants, different laws of physics. This landscape of possibilities, as it is called, implies a multiverse, a vast ensemble of universes with varying properties. Our universe would be just one among countless others, distinguished by the fact that its properties allow for complexity and observers. This idea is highly speculative and controversial. It makes predictions that may be untestable, but it takes seriously the implications of inflation and quantum mechanics, following the logic of these theories to its conclusions. Whether or not the multiverse exists, the universe we observe is remarkable enough. The intergalactic space within our observable universe contains wonders that challenge our imagination and our understanding. Dark matter halos, invisible yet structuring galaxies, hot ionized gas in cosmic filaments, glowing faintly in X-rays, magnetic fields threading through the void, generated by processes we still debate. Cosmic rays accelerated to impossible energies, streaming through intergalactic space. Neutrinos carrying information from the cores of exploding stars. Gravitational, waves rippling through space-time, announcing the collisions of massive objects. All of this is happening in the darkness, in the silence, in the cold between galaxies. It is a realm of extraordinary activity despite its apparent emptiness. Nothing in intergalactic space happens quickly by human standards. The gas in cosmic filaments flows at speeds of hundreds of kilometers per second, fast by terrestrial measures, but slow compared to the distances involved. It takes millions of years for gas to flow along a filament into a galaxy. It takes billions of years for galaxies to merge. The cosmic web evolves on timescales that are geological to us, yet fleeting from the perspective of cosmic history. We are observing snapshots in this slow evolution. When we look at the universe today, we see it at one moment in its history, roughly 13.8 billion years after the Big Bang. The structures we observe are products of all the evolution that has occurred up to this point. But the evolution is not over. Stars are still forming. Galaxies are still merging. The cosmic web is still evolving, responding to the competing influences of gravity and expansion. In the future, the universe will continue to change, becoming different from what it is now, just as the present is different from the past. If we could watch the universe in fast forward, speeding through billions of years in moments, we would see intergalactic space as a dynamic, flowing realm. Gas would stream along filaments like rivers. Galaxies would dance around each other, in clusters, some colliding and merging in brilliant bursts of star formation. The voids would expand, growing larger as dark energy drives acceleration. The cosmic web would stretch and thin, its filaments becoming more tenuous. Over trillions of years, we would see the universe evolving toward its ultimate fate, whatever that may be. But we cannot watch in fast forward. We experience time at its natural pace, 1 second per second, and the cosmic evolution is imperceptibly slow from our perspective. The universe appears static, unchanging, eternal. Only through careful observation and measurement can we detect the slow changes, the expansion, the evolution. And only through theoretical understanding can we project backward to the universe's beginning and forward to its end. This ability to reconstruct cosmic history from present observations is one of the great achievements of modern cosmology. By observing galaxies at different distances, and hence different times in the past, astronomers can trace the history of star formation and galaxy evolution. By measuring the properties of the cosmic microwave background, they can learn about conditions in the very early universe. By studying the abundances of elements, they can test theories of nucleosynthesis in the first minutes after the Big Bang. By mapping large-scale structure, they can infer the properties of dark matter and dark energy. Each observation is a piece of a vast puzzle. Assembling the pieces requires not just data, but theoretical frameworks, models that connect observations to underlying physics. The standard cosmological model, known as lambda-CDM, provides this framework. Lambda represents the cosmological constant, or dark energy. CDM stands for cold, dark matter particles that move slowly compared to the speed of light. The model includes ordinary matter, photons, neutrinos, and the dynamics of cosmic expansion. It has been remarkably successful in explaining a wide range of observations, from the cosmic microwave background to the large-scale structure to the acceleration of expansion. Yet the model has limitations and unresolved questions. The nature of dark matter and dark energy remain unknown. The model does not explain why the cosmological constant has its observed value. It does not fully account for some small-scale structures observed around galaxies. Extensions and modifications have been proposed to address these issues, but the basic lambda CDM framework remains the standard against which observations are compared. Intergalactic space is where many tests of the model occur. The distribution of matter in cosmic filaments and voids constrains the properties of dark matter. The expansion rate measured from distant supernovae constrains dark energy. The temperature and ionization state of the intergalactic medium constrain the history of radiation from stars and quasars. Every new observation adds information, refining our understanding, sometimes confirming predictions, and sometimes revealing surprises. One recent surprise has been the measurement of the Hubble constant, the current rate of cosmic expansion. Different methods of measuring this value have yielded slightly different results, a discrepancy known as the Hubble tension. Measurements based on the cosmic microwave background yield a lower value than measurements based on observations of nearby galaxies and supernovae. The difference is small but statistically significant, and it persists despite careful checks and improvements to both methods. This tension might indicate new physics, something not included in the standard model, or it might be due to subtle systematic errors in one or both measurement methods. Resolving this tension is a major goal of current cosmological research, and the answer will likely involve better understanding of intergalactic space and how it affects our observations. The darkness between galaxies thus remains an active frontier of research. It is not fully explored, not completely understood. Each new telescope, each new observation, each new simulation reveals more details, raises new questions, challenges old assumptions. This is as it should be. Science advances by questioning, by testing, by seeking ever deeper understanding. The apparent emptiness of intergalactic space invites exploration precisely because it is not empty, because it holds secrets about the nature of the universe. In our imagined journey through this space, we have traveled far from any galaxy, immersed ourselves in darkness, contemplated the vast scales and ancient histories written in sparse gas and invisible dark matter. We have considered the structures and processes that govern this realm, from cosmic filaments to magnetic fields, from dark energy to gravitational waves. We have reflected on the philosophical implications, the questions of existence and meaning that arise when confronting cosmic vastness. Now, as our meditation draws toward its close, we might allow ourselves to simply be here, in this imagined darkness, without analysis or explanation, to experience, as much as imagination allows, the profound solitude of intergalactic space, the silence that is not empty but full of information, the darkness that is not absence but presence, the cold that is not death but the natural state of a universe in expansion, the isolation that is not loneliness but connection through the universal laws of physics. In this darkness, you would be far from home, separated from Earth by distances that dwarf human comprehension. Yet you would not be outside the universe. You would be within it, part of it, subject to its laws. The same gravity that shapes galaxies would pull on you. The same expansion that drives galaxies apart would stretch the space around you. The same cosmic microwave background that bathes all of space would surround you with its ancient light. You would be connected to the entire cosmos through these universal phenomena. And in a deeper sense, you are always in this space. The atoms of your body came from stars, and those stars formed from gas that once drifted through intergalactic space. The water you drink contains hydrogen from the Big Bang, atoms that may have spent billions of years in the intergalactic medium before becoming part of Earth. The iron in your blood was forged in a supernova, perhaps ejected into intergalactic space, before being incorporated into the molecular cloud that formed our solar system. You are literally made from the universe, assembled from its elements, animated by its energy. This connection makes intergalactic space less alien. It is part of the same continuum that includes stars and planets and life. The darkness between galaxies is not separate from the light within them. They are aspects of a single whole, the universe in its entirety. from the densest neutron star cores to the emptiest voids. All of it governed by the same physics, all of it evolved from the same beginning, all of it heading toward the same future. The future of intergalactic space is written in the equations of cosmology, though with uncertainties that reflect the limits of our current understanding. If dark energy remains constant, as current observations suggest, then the expansion will continue to accelerate. The space between galaxies will grow. Galaxies that are now visible will recede beyond our cosmological horizon, their light redshifted into undetectability. In 100 billion years, an observer in our galaxy would see only the local group of galaxies, the small cluster that includes the Milky Way and Andromeda, and a few dozen smaller companions. Everything else would have been carried away by expansion, vanished beyond the horizon of observation. In that distant future, intergalactic space will be even emptier than it is today. The thin gas of the intergalactic medium will be stretched thinner still. Dark matter structures will persist, but they will be isolated, each cluster trapped in its own island of space. The cosmic web will have dissolved, its filaments stretched beyond recognition. The voids will have expanded to encompass nearly everything. A future astronomer in that era, if such beings exist, would observe a very different universe from ours. They would see a handful of nearby galaxies, all gravitationally bound together, surrounded by absolute darkness in every direction. They might conclude that their local cluster is the entire universe, unaware of the vast cosmos that lies beyond their horizon. This scenario illustrates how privileged our current epoch is. We live at a time when the universe reveals its full structure. The cosmic web is still visible. Distant galaxies can still be observed. The cosmic microwave background still carries clear information about the early universe. In the far future, much of this information will be inaccessible. Dark energy will have erased the evidence of the larger cosmos from view. Future civilizations, if they arise, will have a harder time reconstructing cosmic history. They will lack the observational evidence that we take for granted. This realization adds urgency to cosmological research. We have a window of opportunity, measured in billions of years, to observe and understand the universe in its full complexity. After this window closes, some knowledge will become permanently inaccessible. We are fortunate to exist in an era when the universe is old enough to have developed complexity and life, yet young enough that the evidence of its history and structure is still available to observation. Yet even as dark energy erases distant galaxies from view, the universe will continue to evolve in other ways. Within isolated galaxy clusters, gravitational interactions will continue. Galaxies will merge over time, eventually coalescing into single giant elliptical galaxies. In our local group, the Milky Way and Andromeda are already on a collision course. In about 4 billion years, they will merge, their stars and gas clouds intermingling in a process that will take hundreds of millions of years. The result will be a single large elliptical galaxy, sometimes called Milkomeda, containing all the stars of both former galaxies. Star formation will continue in these merged galaxies for a while as gas clouds collide and compress, triggering new stellar births. But eventually the gas supply will run out. Stars will consume the available hydrogen and helium, converting it into heavier elements and radiation. No new stars will form. The galaxies will begin to fade as their stars age and die. Low-mass stars like red dwarfs can burn for trillions of years, but even they will eventually exhaust their fuel. High-mass stars will have died long before, exploding as supernovae or collapsing into black holes. In the very distant future, perhaps 100 trillion years from now, star formation will have ceased throughout the universe. The era of stars, the bright epoch in which we currently live, will have ended. Galaxies will contain only stellar remnants. White dwarfs, the cooling cores of former sun-like stars, will be the most common objects. Neutron stars, the collapsed cores of massive stars, will orbit through the darkness. Black holes of various masses will lurk throughout, having consumed or accreted matter over the eons. Brown dwarfs, failed stars that never achieved full fusion, will drift through space, cooling gradually. Intergalactic space in this far future will be colder and darker than ever. The cosmic microwave background will have been stretched by expansion to even longer wavelengths, cooling to a fraction of a degree above absolute zero. The thin gas that currently exists between galaxies will have been almost entirely consumed, pulled into galaxy clusters, or dispersed by expansion into such low densities that it becomes effectively non-existent. Dark matter will still be present, still structuring space through gravity, but with nothing luminous to reveal its presence. This is often called the degenerate era, a time when the universe is dominated by degenerate matter in exotic quantum states like those found in white dwarfs and neutron stars. It is a dark era, but not a dead one. These stellar remnants will slowly evolve. White dwarfs will cool gradually, taking longer than the current age of the universe to reach equilibrium with the cosmic microwave background. Neutron stars will cool more quickly, becoming dark and nearly invisible. Occasional collisions between stellar remnants will release energy, brief flashes in the darkness. Black holes will occasionally accrete matter, releasing energy as the matter spirals inward. In this era, intergalactic space will be the dominant component of the universe by an even larger margin than today. The isolated galaxy clusters will be tiny islands in an ocean of expanding emptiness. The distances between these islands will be so vast that light could never cross them, even given infinite time, because the space between is expanding faster than light can traverse it. Each cluster will be alone, causally disconnected from all others, evolving in isolation toward its own ultimate fate. After the degenerate era comes an even stranger epoch, sometimes called the black hole era. Over immense timescales, stellar remnants in galaxies will interact gravitationally. Some will be ejected from their galaxies, flung into intergalactic space by gravitational slingshot interactions. Others will gradually lose energy to gravitational radiation and spiral toward the center of their galaxy, eventually being consumed by the central supermassive black hole. Over timescales of perhaps 100 million trillion years, galaxies will evaporate, their constituent objects either ejected into intergalactic space or consumed by central black holes. The ejected objects will drift through intergalactic space forever, cooling in the darkness, interacting with nothing. The black holes will remain, having grown massive by consuming a significant fraction of their host galaxy's mass. These black holes will be the dominant objects in the universe, containing most of the matter that has not been ejected. But even black holes are not eternal. Stephen Hawking showed that black holes emit radiation through a quantum process that occurs near their event horizons. This Hawking radiation is incredibly faint for large black holes, with temperatures far below the cosmic microwave background. But as the universe expands and cools, eventually the cosmic microwave background temperature will drop below the Hawking temperature of even supermassive black holes. At that point, black holes will begin to radiate more energy than they absorb, and they will slowly evaporate. The evaporation process is extraordinarily slow. A solar mass black hole takes about 10 to the 67th power years to evaporate. A supermassive black hole might take 10 to the 100th power years or longer. These timescales are so vast that they lose meaning in any human context. They are numbers, mathematical abstractions, but the physical processes they describe are real. Over these immense timescales, black holes will evaporate completely, converting their mass into radiation that disperses into intergalactic space. After the black holes evaporate, the universe will enter its final state, sometimes called the dark era. All that will remain will be a thin soup of elementary particles, photons, neutrinos, and perhaps dark matter particles, all spread through an ever-expanding space. The density will approach zero as expansion continues. The temperature will approach absolute zero. No structures will remain. No complexity will be possible. The universe will have reached a state of maximum entropy, where no further evolution or change is possible. Intergalactic space, in this ultimate future, will have become everything. The distinction between intergalactic space and galactic space will have disappeared because there will be no galaxies. There will be only space, vast and empty and cold, expanding forever, containing only the most diffuse possible distribution of matter and energy. This is the heat death of the universe, the ultimate consequence of the second law of thermodynamics applied on cosmic scales. This far future is speculative, based on our current understanding of physics. There are uncertainties. We do not know if protons are stable or if they decay on very long timescales. If protons decay, then even before black holes evaporate, all ordinary matter will have disintegrated into lighter particles and radiation. We do not know if dark matter particles are stable, or if they too might decay or annihilate. We do not fully understand dark energy or whether its properties might change over time. New physics beyond our current theories might alter the ultimate fate of the universe in ways we cannot predict. But based on what we know now, The darkness between galaxies, the intergalactic space we have been contemplating, represents the future of the entire universe. The emptiness will grow, the structures will dissolve, the complexity will decrease. The universe is heading toward a state where intergalactic space is all there is, stretched thin, cooled to near zero, devoid of stars and galaxies and anything we might recognize as structure. This vision of the far future is sobering. It suggests that the current era, with its stars and galaxies and life, is a brief aberration in cosmic history. The universe began in a hot, dense state. It will end in a cold, diffuse state. In between, for a cosmically brief period, conditions allowed for complexity, for stars to shine, for galaxies to form, for life to emerge. We exist in this brief window. We are temporary, as is everything we observe. Yet there is something profound in this very temporariness. The fact that the universe has given rise to complexity, even briefly, is remarkable. The fact that matter can organize itself into stars and galaxies, into planets and life, into consciousness and understanding, demonstrates deep properties of the laws of physics. The darkness between galaxies, the cold future that awaits, makes the present brightness more precious, more worthy of appreciation and study. Some find the ultimate fate of the universe depressing. The inevitability of cosmic heat death can seem to render everything meaningless. If the universe is heading toward a state of maximum entropy, where nothing interesting can happen, then what is the point of anything? This is an ancient philosophical question, given new form by modern cosmology. It is the question of meaning in a universe that appears indifferent to our existence, that will eventually erase all traces of everything we might accomplish. But meaning is not something the universe provides. It is something we create. The fact that stars will eventually burn out does not make their light less real or less beautiful now. The fact that galaxies will eventually dissolve does not make their current structure less worthy of study. The fact that the intergalactic darkness will eventually encompass everything does not diminish the wonder of the cosmos as it exists today, with its rich tapestry of structures and phenomena. In contemplating intergalactic space, we are engaging with something larger than ourselves, larger than our planet, larger even than our galaxy. We are connecting with the universe as a whole, with the vast scales of space and time that define the cosmic context. This connection can be humbling, reminding us of our smallness, but it can also be empowering, reminding us that we are part of something immense and ancient, that we are made from the universe and capable of understanding it. The darkness between galaxies teaches us about scale. It teaches us that most of the universe is empty, that matter is rare, that the bright spots we see are exceptions rather than the rule. It teaches us humility in the face of vastness, but it also teaches us about connectedness, about the universal laws that govern all of space, about the processes that link galaxies through flows of matter and energy and information. Intergalactic space is not a barrier, but a medium. It is the space through which light travels, bringing information from distant regions. It is the space through which gravitational waves propagate, carrying messages about cosmic events. It is the space through which matter cycles, from galaxies to the intergalactic medium and back again. It is the space through which the cosmic web extends, connecting all galaxies in a single vast structure. It is the space in which dark energy operates, driving the expansion that shapes the universe's evolution. Understanding this space requires understanding the universe as a whole. It requires cosmology, the study of the universe's origin, evolution, and ultimate fate. It requires particle physics, to understand the nature of dark matter and the properties of the intergalactic medium. It requires general relativity, to understand gravity and the geometry of space-time. It requires quantum mechanics, to understand the processes in the early universe that seeded structure formation. It requires observational astronomy, to gather the data that tests theories and reveals the cosmos. This interdisciplinary nature of the quest to understand intergalactic space reflects the unity of the universe. The same fundamental laws apply everywhere, from the smallest quantum scales to the largest cosmological scales. The universe is not a collection of separate phenomena, but a unified whole, where everything is connected to everything else through causality and physical law. Studying intergalactic space is studying the universe itself, examining its most prevalent component, the space that fills most of its volume. As our imagined journey through intergalactic space draws toward its conclusion, we might return to where we began. The darkness between galaxies is not empty. It contains matter, thin but present. It contains dark matter, invisible but dominant. It contains energy in the form of radiation, fields, and the mysterious dark energy. It contains structure in the cosmic web, patterns that emerge from gravitational dynamics. It contains history in the ancient light that traverses it. It contains the future, as the expansion driven by dark energy shapes what is to come. This darkness is a place of profound silence and stillness, yet it is not static. Gas flows along cosmic filaments. Space expands. Gravitational waves pass through. Particles stream through. It is a place of extreme cold and low density, yet it is not absent of activity. Sharks heat gas to millions of degrees. Magnetic fields thread through the void. Cosmic rays are accelerated and deflected. It is a place of isolation, where the nearest star is millions of light years away. Yet it is connected to the entire universe through the web of causality. In this darkness, we find some of the deepest mysteries in science. What is dark matter? What is dark energy? How did the universe begin? How will it end? What is the nature of space and time? These questions cannot be answered by studying galaxies alone. The answers lie in intergalactic space, in the properties of the vacuum, in the distribution of invisible matter, in the dynamics of cosmic expansion. The darkness between galaxies is a laboratory for extreme physics. It contains environments we cannot reproduce on Earth, densities lower than any vacuum we can create, temperatures both hotter and colder than we can achieve, magnetic fields stretched across millions of light years, gravitational potentials from concentrations of dark matter. These conditions allow us to test physical theories in regimes inaccessible to terrestrial experiments. The darkness is also a record. Light passing through intergalactic space is modified by what it encounters. Absorption lines reveal the presence of gas. Gravitational lensing reveals dark matter distributions. The cosmic microwave background carries imprints of conditions in the early universe. Each photon that reaches us from a distant source has traveled through billions of years of cosmic history, and its properties encode information about that journey. By studying these photons, we can reconstruct the conditions along their path, learning about the intergalactic medium, about structure formation, about cosmic evolution, and the darkness is a canvas. The structures we see, the galaxies and clusters and filaments, are painted on this dark background. Without the darkness, without the separation, there would be no individual structures. Everything would blur together. The darkness defines and distinguishes. It allows each galaxy to be itself, separate from others, following its own evolutionary path. The cosmic web exists only because intergalactic space exists, providing the volume through which filaments can extend and in which voids can open. Perhaps most importantly, the darkness between galaxies is a reminder of the sublime. The universe is larger, older, and stranger than anything in our everyday experience. The scales involved transcend human intuition. The processes at work operate on timescales from microseconds to trillions of years. The physics ranges from quantum mechanics to general relativity, from particle interactions to cosmic expansion. And yet we can understand it. We have developed the mathematics, the observations, the theories that allow us to comprehend this realm so far beyond our direct experience. This capacity for understanding is itself remarkable. A species confined to a single planet orbiting a single star in a single galaxy has developed the ability to map the cosmos, to measure its properties, to trace its history from the Big Bang to the present, to predict its future evolution billions of years hence. We have sent our telescopes into space and pointed them into the darkness, collecting ancient photons and transforming them into knowledge. We have built particle accelerators and collided particles at high energies, recreating conditions from the early universe. We have developed the mathematics of curved space-time and applied it to describe the universe as a whole. Human curiosity, ingenuity, and persistence have revealed the hidden universe between galaxies. What once seemed to be empty darkness has been shown to be rich with phenomena. What appeared to be mere separation between interesting objects has been recognized as a realm worthy of study in its own right. The story of intergalactic space is still being written. Each year brings new observations, new discoveries, new insights. The darkness holds secrets we have not yet uncovered. In contemplating this hidden universe, we engage in an act of imagination and reason. We cannot physically travel to intergalactic space. We cannot touch the intergalactic medium or capture dark matter particles, or feel the pull of dark energy. We can only observe, measure, calculate, and infer. Yet through these indirect methods, we have built up a detailed picture of this realm. We know its properties better than we know many places on our own planet. We can describe its composition, its temperature, its motion, its evolution with quantitative precision. This is the power of the scientific method. It allows us to transcend the limitations of our senses and our location. It allows us to explore realms we will never physically visit. It connects observation with theory, data with understanding, curiosity with knowledge. The study of intergalactic space exemplifies science at its best, tackling questions that seem unanswerable, finding ways to measure what seems immeasurable, revealing what was hidden. As we conclude this journey through the darkness, let us carry with us an appreciation for the vastness and complexity of the cosmos. The universe is mostly space, mostly darkness, mostly cold and empty by the standards of our terrestrial existence. Yet this space is not nothing. It is structured, dynamic, evolving. It contains mysteries that challenge our understanding. It connects everything we can see in a cosmic web of breathtaking scope. The next time you look up at the night sky, consider the darkness between the stars. That darkness extends outward, past the edge of our galaxy, into intergalactic space. It continues for millions and billions of light years, filled with the phenomena we have explored. Thin ionized gas flowing along cosmic filaments, dark matter structuring space through invisible gravity, dark energy driving the acceleration of expansion, radiation from the Big Bang bathing everything in ancient light, neutrinos streaming through, gravitational waves propagating through space-time itself. All of this exists in the darkness you cannot see, in the spaces between the lights. The universe is larger and stranger than the pinpoints of stellar light suggest. Most of what exists is not visible to our eyes. Most of the cosmos is hidden, dark, mysterious, but it is not unknowable. Through patient observation and rigorous thought, through the development and testing of theories, through technological innovation and collaborative effort, humanity has begun to understand the hidden universe between galaxies. This understanding is provisional, incomplete, subject to revision as new data arrives. Science is not about achieving final answers, but about continually refining our understanding, always remaining open to correction by nature. The universe is the ultimate authority. Our theories must match observation, or they must be changed. This humility before evidence, this willingness to revise beliefs in light of data, is what makes science reliable and progressive. The darkness between galaxies will continue to reveal its secrets as we continue to study it. New telescopes will probe deeper and with greater sensitivity. New detectors will search for dark matter particles and gravitational waves. New simulations will model cosmic evolution with increasing fidelity. New theories will attempt to explain dark energy and integrate it with the rest of physics. The quest to understand intergalactic space is ongoing, driven by curiosity about the universe and our place within it. In the end, studying intergalactic space is about more than understanding the cosmos. It is about understanding ourselves. We are products of the universe. Our existence depends on the structures that formed in intergalactic space, on the matter that flowed from cosmic filaments into galaxies, on the generations of stars that created heavy elements and dispersed them into space, on the formation of a planetary system where life could arise. We are connected to intergalactic space through this chain of causation, through the history written in our atoms, and we are connected through consciousness, through the capacity to observe and wonder and understand. The universe has given rise to beings capable of comprehending it. This is perhaps the greatest mystery of all. How does unconscious matter, following physical laws, organize itself into consciousness? How do we, made of the same atoms as intergalactic gas and dark matter and everything else, possess awareness and thought? These questions lie at the intersection of cosmology, physics, biology, and philosophy. They remind us that understanding the universe includes understanding the emergence of complexity, of life, of mind. The darkness between galaxies, so remote and so empty, is nevertheless part of the story of how we came to exist and how we came to be able to contemplate our origins. It is part of the cosmic heritage that every human shares. We are all citizens of the universe, inhabitants of a planet orbiting a star in a galaxy suspended in the cosmic web. The intergalactic darkness surrounds us, separates us from other galaxies, and connects us to the larger cosmos of which we are an infinitesimal part. Let this knowledge settle gently into awareness. The vastness need not be terrifying. The darkness need not be depressing. Instead, let it inspire wonder. The universe is more magnificent than we imagined. It extends beyond what we can see, contains more than we can directly detect, operates according to laws we are still working to understand. We have the privilege of existing in this universe, of being able to study it, of adding our small contributions to the accumulated knowledge of our species. The hidden universe between galaxies is not truly hidden anymore. We have revealed it through observation and reason. We have mapped its large-scale structure. We have measured its contents. We have traced its history and predicted its future. This revelation is one of humanity's great achievements, a testament to our capacity for curiosity and understanding. And yet, so much remains to be learned. The darkness still holds secrets. The mysteries of dark matter and dark energy remain unsolved. The ultimate fate of the universe remains uncertain. These unknowns are not failures, but opportunities. They are invitations to continue exploring, to keep questioning, to push the boundaries of knowledge ever outward. Each generation of scientists builds on the work of those who came before, adding new observations, developing new theories, refining our understanding. The study of intergalactic space will continue as long as there are curious minds to wonder about the cosmos. And perhaps, in some distant future, if civilizations persist for long enough, humanity or its descendants might actually venture into intergalactic space. Not in the near future, not with any technology we currently possess or can foresee, but on cosmic timescales, anything not forbidden by physical law is possible. Perhaps one day, beings evolved from humanity will travel between galaxies, not as I have in imagination, but physically, crossing the vast intergalactic gulfs in ships we cannot yet conceive. They would experience directly what we can only observe indirectly. They would float in the true darkness between galaxies, surrounded by the silent void, witnessing firsthand the phenomena we have described. But until that distant time, if it ever comes, we must be content with remote observation and theoretical understanding. We must piece together the nature of intergalactic space from the photons that reach our telescopes, from the mathematical elegance of our theories, from the computational power of our simulations. This indirect approach has served us well. It has revealed a hidden universe of astonishing complexity. It has shown us that the darkness is not empty, but full, not simple but intricate, not separate from us, but intimately connected to everything we are and everything we know. The journey through intergalactic space is ultimately a journey into the nature of reality itself. It takes us to the limits of the observable universe and to the limits of our understanding. It confronts us with mysteries that may not be solved for generations, if ever. It humbles us with the immensity of scales and the poverty of our cosmic significance. But it also elevates us, demonstrating that creatures like us, evolved on a small world, can nonetheless comprehend the cosmos, can reach out with our minds and instruments to touch the fabric of reality itself. As you drift now in this imagined darkness, far from any galaxy, suspended in the cosmic web, surrounded by the faint glow of distant islands of light, take a moment to simply be present to the magnitude of it all. The silence, the cold, the vastness, the age, the slow cosmic processes operating on timescales that dwarf human history, the invisible dark matter structuring everything, the mysterious dark energy driving expansion, the ancient light passing through from the depths of time, the quantum fields that permeate even this seeming emptiness, the laws of physics, elegant and universal, governing every interaction, every motion, every change. All of this is real. All of this exists, not just in imagination, but in actuality, in the universe beyond our Earth. Intergalactic space is out there, vast beyond comprehension, filled with phenomena we have described and others we have yet to discover. It is the dominant component of the cosmos, the space that fills most of the universe's volume. And though we may never visit it physically, we have visited it intellectually. We have mapped it, measured it, understood something of its nature. This understanding is a gift, hard-won through centuries of observation and thought. It is a testament to human curiosity and capability. It connects us to the universe in a profound way, making us not just products of the cosmos, but comprehenders of it. We are the means by which the universe knows itself, the way that unconscious matter has organized itself into consciousness, and then turned that consciousness back upon its origins to understand how it came to be. The hidden universe between galaxies is hidden no longer, revealed by science to be a realm of extraordinary richness. What appears dark to the eye shines brightly in our understanding. What seems empty is full. What feels remote is intimately connected to us through the web of cosmic causality. The darkness between galaxies is part of our heritage, part of our story, part of the grand narrative of the universe evolving from simplicity to complexity. And so, as we return from our imagined journey, drifting back toward our own galaxy, toward our solar system, toward Earth, we carry with us a deeper appreciation for the cosmos. The universe is not just the stars we see, but the darkness between them. It is not just the galaxies, but the vast intergalactic spaces that separate and connect them. It is not just what we can see, but also what we can infer, the dark matter and dark energy that dominate the cosmic budget, yet remain mysterious. The hidden universe between galaxies invites us to look beyond the obvious, to seek understanding of what is not immediately apparent, to use our minds and our tools to reveal the invisible. It challenges us to think on cosmic scales, to grapple with numbers so large and small they resist intuition, to accept that the universe is stranger than we imagined yet still comprehensible. In the silence and the darkness, in the cold and the vastness, the universe continues its slow evolution. Stars burn, galaxies merge, the cosmic web evolves, expansion accelerates, and on at least one small world, beings have emerged who can observe all of this, who can wonder about it, who can work to understand it. That fact, that consciousness has arisen and turned its attention to the cosmos, is itself a cosmic phenomenon worthy of wonder. The darkness between galaxies is not separate from the story of consciousness. It is part of the context in which we exist, part of the universe that gave rise to us. Understanding intergalactic space is part of understanding ourselves, our origins, our place in the vast cosmic tapestry. We are here now, able to contemplate these mysteries. That is a privilege and a responsibility. The privilege to witness the universe in this era of its evolution, when it is both old enough to be interesting and young enough to be observable. The responsibility to use our brief time to learn what we can, to push back the boundaries of ignorance, to add to humanity's collective understanding. The hidden universe between galaxies will outlast us by trillions of years. Long after our sun has burned out, long after our galaxy has merged with others, long after everything we know has transformed beyond recognition, intergalactic space will still be there, still expanding, still evolving according to physical law. The cosmos will continue whether or not anyone is there to observe it. But for now, we are here. We can observe, we can understand, and in doing so, we fulfill a unique role in the universe. The role of conscious observer, of comprehender, of seeker after truth. Let the darkness between galaxies inspire not fear, but wonder. Let the vastness inspire not despair, but curiosity. Let the mysteries inspire not frustration, but determination to understand. The universe has given us the capacity to comprehend it. The hidden universe between galaxies is no longer hidden, revealed to be a realm as rich and complex as any other part of the cosmos. Worthy of study, deserving of appreciation, central to understanding the universe as a whole. In the end, the darkness and the light are one. They are aspects of the same universe, governed by the same laws, connected by the same history, heading toward the same future. The galaxies that blaze with the light of billions of stars exist in relation to the intergalactic voids. The structures emerge from the interplay of gravity and expansion, of dark matter and dark energy, of matter and space-time. Understanding any part requires understanding the whole. The hidden universe between galaxies is not peripheral but central, not empty but full, not separate but integrated into everything we know about the cosmos. And so our journey ends where it began, with an appreciation for the darkness, for the spaces between, for the hidden realms that fill most of the universe. May this exploration bring a sense of peace, a calm acceptance of our place in the vastness, an appreciation for the privilege of existence and consciousness. The universe is ancient and vast, cold and dark, yet it has given rise to warmth and light, to complexity and life, to consciousness and understanding. We are part of that story, participants in the cosmic drama, witnesses to the universe in its current state. As you close your eyes and let sleep approach, carry with you the images of cosmic filaments stretching across the darkness, of distant galaxies glowing softly in the void, of invisible dark matter structuring space, of the expansion carrying everything apart, of the ancient light from the Big Bang bathing all of space, of the slow cosmic evolution that continues across billions of years. These images, born of science and imagination, connect us to something larger than ourselves, to the universe that contains us and all we know. Rest now in the darkness, in the cosmic silence, in the knowledge that you are made of stardust, that your atoms have journeyed through space and time, that you are the universe experiencing itself. Let the vastness bring perspective, the darkness bring peace, the silence bring rest. The hidden universe between galaxies continues its slow evolution, indifferent to our concerns, following its own trajectory toward whatever future awaits. And that is as it should be. We are here now, able to observe and wonder and understand, and that is enough. The cosmos is patient. The darkness between galaxies will still be there tomorrow and the day after, and for billions of years to come. There is no urgency, no rush. The universe unfolds at its own pace, and we are privileged to witness this moment in its history. Let that knowledge bring comfort and wonder as consciousness fades into sleep, as thoughts dissolve into dreams, as awareness merges with the darkness that surrounds us all, the darkness between stars, between galaxies, the darkness that is not empty but full, not ending but ongoing, not separate but connected to everything that is. Rest now, traveler through the cosmic void, and know that you have touched, if only in imagination, the hidden universe between galaxies, the realm of dark matter and dark energy, of cosmic filaments and voids, of ancient light and future expansion, of mysteries unsolved and wonders revealed. The journey has brought understanding, and understanding brings peace. The universe continues, vast and dark and beautiful, and we are part of it, always and forever, connected through our atoms to all that was and is and will be. In the deepest reaches of intergalactic space, where our imagined journey has taken us, there exists a quality of existence that transcends the physical phenomena we have described. It is the quality of timelessness, of being suspended in a moment that stretches across billions of years. Here, where change occurs so slowly as to be imperceptible on human scales, the universe reveals its most fundamental nature. It is not a place of events, but a place of being, where the present moment extends infinitely in all directions, where past and future merge into an eternal now. This timelessness is not an illusion. It is a real property of intergalactic space, emerging from the combination of vast distances and slow processes. When the nearest star is millions of light years away, when the density of matter is measured in single atoms per cubic meter, when the temperature approaches absolute zero, the frenetic activity of terrestrial existence gives way to something approaching stillness. Not perfect stillness, for motion and change never entirely cease, but a stillness so profound that it invites contemplation of the eternal. In this stillness, we might consider the nature of time itself. On Earth, time is marked by cycles, day and night, the seasons, the beating of hearts, the decay of radioactive elements, the aging of living things. These cycles give time its texture, its forward motion, its inexorable progression. But in intergalactic space, most of these markers are absent. There is no day or night, for there is no nearby star to define them. There are no seasons, for there is no orbit around anything. There is no life to age and die. Even radioactive decay proceeds so slowly and involves so few atoms in any given volume that it provides no meaningful marker of time's passage. What remains are the most fundamental processes, the expansion of space itself, stretching the fabric of the universe at a rate determined by its energy content, the slow evolution of the cosmic microwave background, cooling as expansion redshifts its photons to ever longer wavelengths, the gradual clustering of dark matter under gravity's patient pull, the flow of sparse gas along cosmic filaments, moving at speeds that seem fast by human standards but are glacial compared to the distances involved. These processes mark time in intergalactic space, but they do so with such deliberation that time itself seems to slow, to stretch, to become something different from what we experience. Perhaps this altered experience of time is closer to the universe's own perspective, if such a thing can be said to exist. The universe does not experience time the way we do. It does not rush or wait. It simply is, moment by moment, each configuration of matter and energy flowing inevitably from the previous one according to physical law. The apparent flow of time, the distinction between past and future, emerges from the second law of thermodynamics, from the increase of entropy, from the arrow of time that points from order toward disorder. In intergalactic space, this arrow of time is visible in cosmic evolution. The universe began in a state of high energy density and low entropy. As it expanded and cooled, as structures formed and stars ignited, entropy increased. Each nuclear reaction in every star increases the universe's total entropy, converting low-entropy hydrogen into higher-entropy helium and heavier elements, releasing photons that disperse into space. Each galaxy merger, each interaction of particles, each flow of gas increases entropy. The universe is running down, moving inexorably toward maximum entropy, toward the heat death we discussed earlier. But this running down occurs over such vast timescales that it becomes almost abstract. In any given moment, in any particular region of intergalactic space, change is nearly imperceptible. The local entropy might fluctuate slightly, gas might flow one way or another, but the overall trajectory is so gradual as to seem static. This creates a paradox of perception. The universe is dynamic, evolving, changing constantly. Yet on any timescale we can directly experience, it appears eternal and unchanging. This paradox reflects the limitations of human perception. We are adapted to sense and respond to changes that occur on timescales of milliseconds to years. Our nervous systems are tuned to detect motion, variation, novelty. We are ill-equipped to perceive processes that unfold over millions or billions of years. Yet these slow processes are as real and as important as the fast ones. The drift of continents, the evolution of species, the dance of stars in galaxies, the expansion of the universe itself, all proceed at rates beyond our direct perception but shape everything we know. In intergalactic space, these limitations of perception become particularly acute. Here, the timescales of change are so long that even recorded human history, spanning thousands of years, is insufficient to detect any difference. The universe in intergalactic space today looks essentially the same as it did when our ancestors first looked up at the sky and wondered. The cosmic web has the same structure. The galaxies occupy the same positions, apart from tiny proper motions. The expansion rate has changed imperceptibly. On human timescales, intergalactic space is eternal. Yet on cosmic timescales, everything is in flux. The galaxies we see are not where they appear to be, having moved in the billions of years their light took to reach us. The cosmic web is different now from what we observe, having evolved during the light travel time. The universe is older now than when the photons we detect were emitted. We are always observing the past, never the present. The present moment in intergalactic space, the configuration of matter and energy right now in those distant regions, is forever hidden from us, unknowable, separated by the finite speed of light and the vast distances involved. This creates a strange relationship between observer and observed. When we study intergalactic space, we are studying history, not the present. We are archaeologists of the cosmos, digging through layers of time encoded in light of different wavelengths and origins. The deepest observations show us the universe as it was in its infancy. Shallower observations reveal more recent epochs. Nearby objects show us the relatively recent past. But the true present moment in distant intergalactic space remains inaccessible, hidden beyond the light travel time. In a sense then, intergalactic space exists in multiple times simultaneously. The light reaching us from various distances shows us the universe at various ages. A photon from a galaxy 10 million light-years away shows us that region as it was 10 million years ago. A photon from 10 billion light-years away shows us that region as it was 10 billion years ago. Both photons arrive at our telescopes at the same moment, carrying information from different cosmic epochs. The universe, as we observe it, is a palimpsest of times, layered one upon another, all present in our detectors simultaneously. This layering of times reveals cosmic evolution. By comparing observations at different distances, astronomers can see how the universe has changed. The proportion of galaxies actively forming stars was higher in the past than it is now. The universe was denser in the past, with galaxies closer together. The intergalactic medium was less enriched with heavy elements in the past. Dark energy was less dominant in the past, when the universe was smaller and denser. All of these changes are visible in the layered light from intergalactic space, each photon a messenger from a specific time and place. The patient accumulation of these photons over years of observation builds up a picture of cosmic history. Each observation adds detail, refines measurements, tests predictions. The picture that emerges is one of remarkable consistency. Independent lines of evidence point to the same cosmic timeline, the same sequence of events from the Big Bang to the present. This convergence of evidence gives us confidence that we understand, at least in broad outline, the history of intergalactic space and the universe as a whole. Yet mysteries remain, gaps in our understanding that hint at deeper physics we have not yet grasped. The nature of the initial singularity, the state of the universe at time zero, remains opaque. General relativity predicts that the universe began in a state of infinite density and temperature. But this prediction likely indicates the breakdown of the theory rather than physical reality. Quantum effects must have been important in the earliest moments, but we lack a complete theory of quantum gravity to describe them. The universe's initial conditions, the specific values of physical constants, and the particular configuration of matter and energy remain unexplained. Why these values and not others? Why is there something rather than nothing? These questions probe the foundations of existence itself. Intergalactic space in its vast emptiness seems an unlikely place to seek answers to such profound questions. Yet it is precisely here, in the universe's most common state, that clues to the deepest mysteries may be found. The uniformity of the cosmic microwave background, visible from all points in intergalactic space, provides evidence for inflation and hints at the quantum nature of the very early universe. The distribution of dark matter in cosmic filaments constrains models of particle physics beyond the standard model. The value of dark energy, manifest in the acceleration of expansion observable across intergalactic distances, points to physics we do not yet understand. The darkness holds clues to the light, to the nature of reality itself. As consciousness drifts in this contemplation, as the mind moves between scales from the quantum to the cosmic, from the instant to the eternal, from the particular to the universal, a sense of unity emerges. The universe, for all its apparent diversity, is fundamentally one thing. Matter and energy are equivalent, related by Einstein's famous equation. Space and time form a unified spacetime, curved by matter and energy. Forces that seem distinct at low energies unify at high energies. The quantum and classical realms, though described by different mathematical frameworks, govern the same underlying reality. The universe is not a collection of separate phenomena, but a single, unified, evolving system. Intergalactic space embodies this unity. It is not separate from galaxies, but continuous with them. The same laws govern both. The same matter cycles between them. The same forces act throughout. The apparent emptiness of intergalactic space and the apparent fullness of galactic cores are extremes of the same continuum, different manifestations of matter's distribution in space. Neither is more real or more fundamental than the other. Both are necessary components of the cosmic whole. This holistic view of the cosmos has been slow to develop in human thought. Ancient cosmologies saw the universe as divided into distinct realms: earth and sky, terrestrial and celestial, mortal and divine. The scientific revolution began to erase these divisions, showing that the same physics applies on Earth and in the heavens. The discovery of the cosmic distance scale revealed that nebulae are galaxies like our own, that the universe is far larger than previously imagined. The recognition of cosmic expansion showed that the universe has a history, that it evolves over time. Each discovery has reinforced the unity of the cosmos, the continuity of physical law across all scales and epochs. Intergalactic space represents perhaps the ultimate test of this unity. Here, far from any galaxy, in conditions utterly unlike anything on Earth, do the same laws still apply? All evidence says yes. Light travels at the same speed. Atoms have the same properties. Gravity follows the same inverse square law, modified by general relativistic corrections. The cosmic microwave background has the same temperature in all directions. The universe looks the same from every vantage point, at least on large scales. This uniformity, this universality of physical law is perhaps the most profound discovery of modern science. It means that knowledge gained anywhere is applicable everywhere. It means that the universe is comprehensible in principle, if not always in practice. The comprehensibility of the universe is something we often take for granted, yet it is deeply mysterious. Why should the universe be describable by mathematics? Why should the laws of physics be simple enough for human minds to grasp? Why should the patterns we observe on Earth extend across intergalactic space? These questions have no obvious answers. The universe could have been chaotic, lawless, incomprehensible. That it is not, that it reveals itself to patient observation and careful reasoning, is a gift whose origins we do not understand. Some have argued that this comprehensibility is not coincidental, that the universe must be comprehensible because otherwise we would not exist to comprehend it. This anthropic argument suggests that only in a universe with stable laws, with physics that allows for complexity, could observers evolve to ask these questions. We observe a comprehensible universe because incomprehensible universes do not produce observers. This argument has some merit, but it pushes the mystery back rather than resolving it. Why does any universe exist? Why these laws and not others? The anthropic principle explains why we observe what we observe, but not why anything exists to be observed. In the silence of intergalactic space, these philosophical questions resonate with particular force. Here, stripped of the complexity and distraction of terrestrial life, the fundamental nature of existence becomes the primary question. What is this space? What is the vacuum? Is it truly empty, or does it contain fields and virtual particles and dark energy? What is the nature of space-time itself? Is it fundamental, or does it emerge from something deeper, perhaps quantum entanglement or information? These questions probe the boundary between physics and metaphysics, between what we can measure and what we can only speculate about. Modern physics has revealed that the vacuum is not empty in the naive sense. Quantum field theory describes the vacuum as seething with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate almost instantaneously. These virtual particles are not directly observable, but their effects are real and measurable. They contribute to the energy of the vacuum. They modify the properties of particles. They enable processes that would otherwise be forbidden. The vacuum, far from being nothing, is a dynamic medium, the lowest energy state of quantum fields that permeate all of space. In intergalactic space, this quantum vacuum may be the dominant component. The density of ordinary matter is negligible. Dark matter, though more prevalent, is also sparse. What fills the space, what gives it its properties, is the vacuum itself and the fields that inhabit it. The electromagnetic field, the gravitational field, the various quantum fields associated with fundamental particles, all extend through intergalactic space, their lowest energy states defining what we perceive as empty space. But this emptiness has structure, has properties, has energy. It is not nothing. Dark energy may be a property of this vacuum. If the vacuum has a non-zero energy density, if the quantum fields in their ground states possess energy, then this energy would exert gravitational effects. And unlike matter, whose gravity attracts, vacuum energy has negative pressure, causing it to repel gravitationally. This repulsion, acting on cosmic scales, could drive the accelerated expansion we observe. This explanation of dark energy as vacuum energy is elegant, but it faces a severe problem. Calculations of the expected vacuum energy based on quantum field theory yield a value that is many orders of magnitude larger than what we observe. This discrepancy, sometimes called the cosmological constant problem, is one of the worst quantitative predictions in physics. Resolving this problem likely requires new physics, perhaps quantum gravity, perhaps some modification of quantum field theory, perhaps some entirely new principle we have not yet conceived. The darkness of intergalactic space, where dark energy dominates, is telling us that our understanding of the vacuum is incomplete. Something fundamental is missing from our theories. The accelerated expansion is a clue, a signpost pointing toward physics beyond what we currently know. This realization is humbling but also exciting. It means that despite centuries of progress, despite the remarkable success of modern physics in explaining phenomena from subatomic scales to cosmic scales, we are not at the end of discovery. The universe still holds secrets. The darkness still conceals mysteries. There is work yet to be done, questions yet to be answered, discoveries yet to be made. Intergalactic space, far from being well understood dead space between interesting objects, is a frontier where the next revolutions in physics may occur. As the mind drifts in this space of contemplation, as thoughts become less focused and more dreamlike, as consciousness begins the slow descent into sleep, the boundaries between self and universe begin to blur. We are not separate from the cosmos we have been exploring. We are made of its matter, governed by its laws, products of its history. The atoms in our bodies were forged in stars and dispersed into space, perhaps spending time in intergalactic space before being swept up in the formation of our solar system. The energy that animates us comes ultimately from the sun, which derives its energy from nuclear fusion, converting hydrogen into helium and releasing photons. Those hydrogen atoms were created in the Big Bang, as was the space through which everything moves. We are continuous with the universe, not separate from it. The distinction between inside and outside, between self and cosmos, is a convenient fiction, useful for navigating daily life but ultimately illusory. We are local concentrations of complexity in a universe that is mostly simple. We are temporary patterns in the flow of matter and energy, structures that persist for a while before dissolving back into the cosmic flux. This dissolution is not to be feared. It is the natural course of things, the return of complexity to simplicity, of local order to cosmic entropy. In intergalactic space, this cosmic perspective is easier to maintain. Here, far from the concerns and complexities of life, the fundamental simplicity of existence is apparent. Space, time, matter, energy, governed by laws, evolving according to physics. That is all there is, and it is enough. The universe does not need purpose or meaning beyond its own existence. It simply is, moment by moment, configuration by configuration, following the trajectory determined by its initial conditions and the laws that govern its evolution. And yet, within this seemingly purposeless physics, complexity arises. Stars form, galaxies evolve. On at least one planet, perhaps on many, life emerges. Consciousness develops. Meaning is created, not given. Purpose is chosen, not inherent. The universe may be indifferent, but we are not. We care about things. We assign value. We create meaning through our choices and actions and relationships. This meaning is real, even if it is not cosmic. It is human, and that is enough. The darkness between galaxies knows nothing of human meaning. It proceeds according to physics, indifferent to our hopes and fears, our joys and sorrows, our brief moments of consciousness in the cosmic night. This indifference can seem harsh, but it is also liberating. It means we are free to create our own meaning, to define our own values, to choose our own purposes. The universe does not constrain us except through physical law. Within those constraints, everything is possible. As sleep approaches, as thoughts fragment and drift, as the boundary between waking and sleeping blurs, carry with you this sense of cosmic perspective. You are small, yes, infinitesimal compared to the scale of intergalactic space. Your life is brief, a few decades in a universe billions of years old. Your concerns are local, confined to a single planet in a single solar system in one galaxy among hundreds of billions. And yet, you are also remarkable. You are complex, conscious, capable of understanding. You can comprehend intergalactic space despite never visiting it. You can grasp the history of the cosmos despite not witnessing it. You are a way for the universe to know itself, and that is not nothing. Rest now in this knowledge. The cosmos continues, vast and ancient, dark and luminous, simple and complex. It proceeds at its own pace, following its trajectory from the Big Bang toward whatever ultimate fate awaits. You are part of that cosmic story, a brief chapter, but a real one. Your existence matters, if only to you and to those you touch. The universe has given rise to you, and that is a kind of gift, an opportunity to experience and understand and create meaning in the brief span allotted to you. The hidden universe between galaxies will still be there tomorrow, unchanged on any timescale you can perceive. Its mysteries will remain, waiting for future generations to unravel. Its darkness will continue to separate galaxies and define structures. Its expansion will persist, driven by dark energy, carrying everything toward greater isolation. And life, if it exists elsewhere, will continue its own trajectory, perhaps wondering about the cosmos as we do, perhaps creating its own meaning in the face of cosmic indifference. All of this is happening now, has always been happening, will continue to happen long after we are gone. The universe is patient and persistent. It has no urgency, no anxiety, no fear of its ultimate fate. It simply is, moment by moment, following the laws that govern it, evolving from one configuration to the next. We can learn from this patience, this acceptance of what is. We can let go of urgency and anxiety, at least for this moment, and simply rest in being, in existence, in the brief privilege of consciousness. The darkness surrounds us always, whether we acknowledge it or not. Between atoms, there is mostly empty space. Between stars, vast distances. Between galaxies, the intergalactic void we have been exploring. This darkness is fundamental, the ground upon which structure is built, the space in which motion occurs, the medium through which light travels. Without the darkness, there would be no light. Without the emptiness, there would be no form. Without the silence, there would be no sound. The darkness is not opposite to light, but complementary to it, necessary for light to be light, for stars to be stars, for galaxies to be galaxies. In sleep, we return to darkness. Consciousness fades, awareness dims. The self dissolves temporarily into the neural darkness from which it emerged. This nightly dissolution mirrors the cosmic dissolution that awaits all structure eventually. But just as we wake again each morning, consciousness returning with the day, perhaps the universe too is cyclic. Perhaps this cosmic epoch is just one among many. Perhaps dissolution is followed by renewal in patterns we cannot yet discern. These are speculations, but they remind us that endings are also beginnings, that dissolution makes room for new forms, that the cosmos is creative, constantly generating novelty from its simple laws and abundant matter and energy. Rest now, cosmic traveler. Your journey through the hidden universe between galaxies has reached its conclusion. You have contemplated vast distances and ancient times. You have considered dark matter and dark energy, cosmic filaments and voids, expansion and evolution. You have touched, if only in imagination, the most common state of the universe, the darkness that fills most of space. You have reflected on mysteries unsolved and questions unanswered, on the limits of knowledge and the possibilities of future discovery. Carry these contemplations into sleep like seeds that will germinate in the darkness of unconsciousness. Let the vastness bring perspective to petty concerns. Let the timeless quality of intergalactic space bring patience to your hurried life. Let the mysteries remind you that not everything needs to be understood immediately, that some questions are worth living with, pondering over time. Let the unity of the cosmos remind you of your connection to everything, your participation in the grand drama of cosmic evolution. The universe continues its slow dance, galaxies swirling, space expanding, matter flowing from void to filament to galaxy and back again. You are part of this dance, briefly conscious, briefly able to observe and wonder. When consciousness fades in sleep, and ultimately in death, you return to the universe from which you came, your constituent atoms dispersing to join the cosmic circulation once more. This return is not to be feared. It is simply the nature of temporary forms in an evolving cosmos. For now, rest. The hidden universe between galaxies will keep its secrets and its wonders. The darkness will remain dark, yet not empty. The expansion will continue, driven by mysterious dark energy. The cosmic web will evolve, slowly and patiently, following gravity's steady pull. And in scattered pockets of complexity, perhaps on many worlds in many galaxies, consciousness will persist, wandering about the cosmos, seeking to understand, creating meaning in the vast, indifferent universe. You are one instance of this cosmic consciousness, one momentary awakening of matter into awareness. Rest now in that knowledge, at peace with your place in the cosmic order, grateful for the privilege of existence and understanding, content to be a small part of something infinitely larger than yourself. The darkness welcomes you, not as ending, but as rest, not as negation, but as foundation, not as absence, but as potential. Sleep now, traveler, in the cosmic darkness, surrounded by invisible dark matter and mysterious dark energy, suspended in expanding space-time, connected through your atoms to all that is and was and will be. The hidden universe between galaxies cradles you as it cradles everything, indifferently but completely, the context in which all existence unfolds. Rest in this vast context, this ancient cosmos, this continuing evolution. You are home. You have always been home. You are the universe knowing itself, and that is beautiful and enough. The darkness deepens, consciousness dims. Sleep approaches on soft cosmic feet, bringing rest and dreams, dissolution and renewal. The journey ends where it began, in wonder and peace, in darkness and light, in the hidden universe that contains us all. The boundary between waking and sleep becomes permeable now, like the boundary between a galaxy and intergalactic space. Not a sharp edge, but a gradual transition, a fading of one state into another. Thoughts become softer, less defined, drifting like clouds of gas in cosmic filaments, moving without direction, without purpose, simply flowing according to the subtle forces that guide them. This is the liminal space, the threshold between consciousness and unconsciousness, where the mind releases its grip on the structured world and allows itself to float free. In this floating state, the images of intergalactic space merge with the approaching darkness of sleep. The two darknesses are not so different. Both are vast, both are largely empty yet somehow full. Both exist beyond the reach of ordinary perception. Both invite surrender, a letting go of the need to understand, to control, to maintain the boundaries of self. In sleep, as in the cosmic void, the small dissolves into the large, the temporary into the timeless, the particular into the universal. Consider the gift of not knowing. We have spoken much of understanding, of humanity's quest to comprehend the cosmos, but there is also value in mystery, in accepting that some things lie beyond our grasp, at least for now, perhaps forever. The universe does not owe us comprehensibility. The fact that we can understand as much as we do is remarkable, but the vast reaches of what we do not know, the questions we cannot answer, the phenomena we cannot observe, these too have their place. They keep us humble. They remind us that we are not the measure of all things, that reality extends far beyond what we can perceive or conceive. In intergalactic space, this unknowing is particularly acute. We cannot see dark matter. We cannot identify dark energy. We cannot observe beyond our cosmological horizon. We cannot witness the present moment in distant regions, only the ancient past. We cannot predict with certainty the ultimate fate of the universe. These limitations are not failures but boundaries, defining the scope of possible knowledge while hinting at what lies beyond. They create a space for wonder, for speculation, for the imagination to roam freely where observation cannot reach. As consciousness continues its gentle recession, as the mind becomes less engaged with the details we have discussed, and more receptive to the overall feeling, the overall sense of the cosmos allow the specifics to blur. The numbers fade, the technical terms dissolve. What remains is the essence, the core experience of contemplating vastness and darkness and mystery. What remains is the feeling of being small yet connected, temporary yet part of something eternal, conscious yet emerging from and returning to unconsciousness. This feeling has been with humanity since our ancestors first looked up at the night sky and wondered. Before we knew about galaxies and intergalactic space, before we understood cosmic expansion and dark energy, before we had telescopes and equations and simulations, we still felt the pull of the cosmos, the sense of something vast and mysterious beyond our immediate world. That feeling has not diminished with knowledge. If anything, it has deepened. The more we learn, the more we realize how much we do not know. The more we observe, the more mysteries we uncover. The cosmos reveals itself and conceals itself simultaneously, giving us glimpses of its nature while withholding its deepest secrets. In the space between galaxies, this dynamic of revelation and concealment plays out on the largest scales. We can map the cosmic web, but we cannot see the dark matter that defines it. We can measure the expansion, but we cannot explain dark energy that drives it. We can observe the ancient light from the early universe, but we cannot penetrate to the very first moments. Each answer generates new questions. Each discovery opens new territories of ignorance. This is not frustrating, but exhilarating, a sign that the universe is deeper and richer than any finite understanding can encompass. Perhaps this is as it should be. Perhaps the universe is, in some sense, infinite, not just in spatial extent, but in depth of structure, in layers of reality, in complexity of organization. Perhaps no finite mind, no matter how advanced, could ever comprehend it completely. Perhaps the quest for understanding is not meant to reach a final destination, but to be an endless journey, each generation adding its contributions while passing on unsolved mysteries to the next. This perspective transforms the limitations of knowledge from deficits into opportunities, from barriers into horizons, from endings into beginnings. The darkness between galaxies embodies this endless horizon. No matter how far we look, there is always farther to look. No matter how much we understand, there is always more to understand. The cosmos extends beyond observation, beyond comprehension, beyond imagination. It is too large, too old, too complex for any single perspective to encompass. And yet, partial understanding is still understanding. Incomplete knowledge is still knowledge. The fact that we cannot know everything does not diminish the value of knowing something. As sleep draws closer, as thoughts become even more diffuse and dreamlike, as the narrative structure of this contemplation dissolves into pure atmosphere, pure mood, let yourself sink into the darkness like a particle of matter, sinking into a potential well in the cosmic web. There is no resistance, no struggle, only the natural motion of following the gradient from higher to lower energy states, from wakefulness to sleep, from complexity to simplicity, from activity to rest. This motion is not loss, but completion, not ending, but transformation into a different state, equally valid, equally real. In the cosmic web, matter follows similar paths, flowing from voids into filaments, from filaments into galaxies, always seeking lower gravitational potential, always following the gradient created by the distribution of mass and energy. This flow is not purposeful but inevitable, the result of forces acting on matter according to law, yet the result is structure, organization, patterns of extraordinary beauty and complexity. From simple rules and random initial conditions, the universe generates order. From undifferentiated matter and energy, it creates galaxies and stars and planets and life and consciousness. This emergence of complexity from simplicity is one of the universe's most profound characteristics. It occurs at every scale, from the quantum realm where particles emerge from fields, to the cosmic scale where galaxies emerge from the gravitational collapse of dark matter and gas. It occurs in chemistry, where complex molecules emerge from combinations of simple atoms. It occurs in biology, where living systems emerge from complex chemistry. It occurs in neurology, where consciousness emerges from patterns of neural activity. The universe is creative, constantly generating novelty, constantly exploring possibilities within the constraints of physical law. Intergalactic space participates in this creativity. It is not a static backdrop, but an active component of cosmic evolution. Matter flows through it, carrying energy and information. Radiation traverses it, connecting distant regions. Gravitational waves propagate through it, linking events separated by vast distances. The expansion of space itself is a creative process, generating new space between galaxies, stretching the cosmic web, driving the evolution of structure. Nothing in the cosmos is truly passive or inert. Everything participates in the ongoing creative unfolding of the universe. You too participate, though your contribution seems small. The thoughts arising in your mind right now, the contemplation of intergalactic space and cosmic mysteries, the wonder and curiosity you feel, these are the universe becoming aware of itself. Through you, the cosmos observes and reflects on its own nature. Through your consciousness, matter organized into neural patterns experiences something we call awareness. This awareness is fragile, temporary, localized to your brain for a few brief decades, but it is real. It is part of the universe as much as stars and galaxies are. And when your particular instance of consciousness ends, the universe continues, perhaps generating other instances elsewhere, other eyes to observe, other minds to wonder. The continuity of consciousness across individuals and generations creates a larger pattern, a kind of collective awareness that transcends any single lifetime. What you learn, you can share with others. What others have learned, you can receive. Knowledge accumulates across generations, building toward ever greater understanding. This process has been occurring throughout human history, accelerating in recent centuries as science has become more systematic and collaborative. The understanding of intergalactic space we have discussed is not the product of any single mind, but the collective achievement of countless astronomers, physicists, mathematicians, engineers, and thinkers across generations. This collective nature of knowledge reflects the connected nature of the cosmos itself. Nothing exists in isolation. Every particle interacts with fields. Every mass curves space-time. Every event influences others through causal chains that propagate at light speed. The universe is a web of relationships, of influences, of connections extending across space and time. We are nodes in this web, each of us receiving influences from the past and sending influences into the future, each of us connected to every other part through chains of causation that extend to the beginning of time. In intergalactic space, these connections are attenuated but not severed. The gravitational influence of distant galaxies is weak but real. The light from distant sources is faint but detectable. The cosmic microwave background connects all regions of space to the same ancient origin. Even the vast voids are not truly isolated, but embedded in the same space-time, governed by the same laws, participating in the same cosmic evolution. The appearance of separation is deceiving. At a fundamental level, everything is connected. This interconnectedness extends to the quantum realm, where particles can be entangled, maintaining correlations across arbitrary distances. Though this entanglement cannot be used to transmit information faster than light, it reveals that locality is not absolute, that the universe is not built from entirely separate and independent pieces. What happens here is related to what happens there, not through local interactions, but through non-local quantum correlations. The universe is more unified, more holistic than classical physics suggested. Perhaps consciousness too has non-local aspects we do not yet understand. Perhaps awareness is not entirely confined to individual brains, but extends in ways we cannot yet measure or comprehend. These are speculations, not established science, but they arise naturally when contemplating the relationship between consciousness and cosmos, between the subjective experience of awareness and the objective structure of physical reality. The hard problem of consciousness, the question of how subjective experience arises from objective matter, remains unsolved. The darkness of intergalactic space finds its parallel in the darkness of the mind, the unknown territory where matter becomes aware, where neural activity generates the feeling of being someone, of experiencing something. As this journey approaches its natural conclusion, as sleep becomes imminent, as the last threads of narrative dissolve into pure sensation and atmosphere, let all these considerations fade into the background. The details are not important now. The understanding has been achieved, the journey completed. What remains is simply the state of being, the experience of existing in this moment, suspended between waking and sleeping, between the particular and the universal, between the small and the vast. You are here, now, in this moment. Your body rests comfortably, supported and safe. Your breathing is slow and deep, each breath drawing in air, each exhalation releasing tension. Your heart beats steadily, pumping blood through vessels, maintaining the metabolic processes that sustain life. Your nervous system cycles towards sleep, releasing neurotransmitters that quiet activity, dampen sensory input, withdraw attention from the external world. This is natural, inevitable, the body's wisdom asserting itself, guiding you toward the rest you need. In intergalactic space, there is no rest in the biological sense, but there is something analogous. The cosmic web evolves slowly, almost imperceptibly, like someone sleeping deeply, barely moving. The expansion continues, steady and relentless, like breathing, in and out, though in this case only out, only expansion, space growing larger with each passing moment. The dark matter remains dark, invisible, resting in its gravitational potential wells, structuring space without fanfare or announcement. The dark energy permeates everything, subtle and uniform, like the background hum of existence itself, barely noticeable yet ultimately dominant. These cosmic processes proceed without awareness, without intention, without effort. They simply are, the natural unfolding of physical law applied to matter and energy distributed through space. There is no struggle, no striving, no resistance. The universe does not try to expand, it expands. Dark matter does not try to clump, it clumps. Stars do not try to shine, they shine. Everything follows its nature, its inherent tendencies given its composition and circumstances. This is what physicists mean by determinism, the idea that each state of the universe follows inevitably from the previous state according to law. Yet within this determinism, or perhaps alongside it, there seems to be room for novelty, for the emergence of genuinely new patterns and possibilities. Quantum mechanics introduces genuine randomness at the smallest scales. Chaos theory shows that deterministic systems can be unpredictable. Complexity science reveals that simple rules can generate intricate patterns that could not have been foreseen. The universe is deterministic yet creative, lawful yet surprising, predictable yet mysterious. You too embody this paradox. Your brain operates according to physical law, neurons firing in patterns determined by chemistry and electricity. Yet you experience free will, the sense of choosing, of deciding, of being the author of your actions. This apparent contradiction has puzzled philosophers for centuries. Perhaps both perspectives are true, capturing different aspects of a reality too rich to be encompassed by either view alone. Perhaps you are both determined and free, both mechanism and agent, both object and subject. Perhaps the universe itself is like this, both clockwork and creativity, both law and spontaneity, both determined trajectory and open possibility. In the space between galaxies, these questions find their largest expression. Does the universe follow a predetermined path from initial conditions to ultimate fate? Or does genuine novelty emerge? Possibilities become actual. The future remain genuinely open. The expansion seems inevitable, driven by dark energy, pointing toward an ultimate heat death. Yet dark energy is poorly understood. New physics might change predictions. The universe might hold surprises we cannot anticipate. The future is not written, or if it is, we cannot read it. The darkness ahead, temporal as well as spatial, conceals what is to come. But this uncertainty need not cause anxiety. The future will unfold as it will, whether we worry about it or not. Our influence on cosmic evolution is negligible. The expansion will continue regardless of our concerns. Galaxies will merge or separate according to gravity and expansion, indifferent to our preferences. The universe proceeds on its own terms, following its nature, unconstrained by our hopes or fears. This cosmic indifference is not hostile, but neutral, neither for us nor against us, simply indifferent. And there is peace in accepting this indifference. On human scales, our choices matter. Our actions have consequences. We can influence our local environment, our relationships, our communities. This local efficacy is real and important, but on cosmic scales we are insignificant. This insignificance, far from being depressing, can be liberating. It means the universe does not depend on us. It means we are free from cosmic responsibility. It means we can focus on what is within our scope, our lives and loves, our growth and learning, our contributions to the human story, without bearing the unbearable weight of cosmic significance. The darkness between galaxies knows nothing of human drama. It continues regardless. And this continuation, this steady persistence of the cosmos, provides a kind of stability, a backdrop against which human life unfolds. The stars will still be there tomorrow. The galaxies will still spin. The cosmic web will still structure space. This predictability on large scales allows for unpredictability on small scales. Life can be surprising, dramatic, full of unexpected turns. Precisely because the cosmic stage remains stable, the laws unchanging, the basic fabric of reality reliable. As consciousness fades further, as sleep claims you more completely, as the last vestiges of directed thought give way to the free association of dreams, carry with you a sense of gratitude. Gratitude for existence, for consciousness, for the brief opportunity to experience and understand. Gratitude for the universe that gave rise to you, that sustains you, that will receive you back when your time ends. Gratitude for the darkness and the light, for the mystery and the knowledge, for the questions and the partial answers. Gratitude for this moment, this state between waking and sleeping, this peaceful transition from activity to rest. The hidden universe between galaxies, the vast darkness we have explored together, is always there, whether we think about it or not. It does not require our attention to exist. It proceeds according to its nature, eternal on timescales we can perceive. Even as it evolves on cosmic timescales we cannot directly observe. In this sense, it is like consciousness itself, always present in the background, the context in which everything occurs, so fundamental that we often forget to notice it. But you have noticed. You have turned your attention to this darkness, this emptiness that is not empty, this silence that is not silent, this space that is full of phenomena and mystery. You have made the imaginative journey from Earth to the depths of intergalactic space, contemplating what exists there, what it means, how it connects to everything else. This contemplation has value even if it changes nothing about the cosmos itself. It enriches your understanding, it expands your perspective, it connects you to something larger than yourself. And these internal changes, though invisible and intangible, are real and meaningful. Now release it all. Release the effort of understanding. Release the journey and its discoveries. Release the questions and the mysteries. Release even the sense of self that has been contemplating these things. Let it all dissolve into the approaching darkness of sleep, where boundaries blur and structures soften and everything merges into the undifferentiated flow of unconscious process. This dissolution is temporary. You will wake again, consciousness returning, the self reforming, the world appearing once more in all its specificity and detail. But for now, let go. Let sleep come. Let the darkness take you gently, completely, as it takes everything eventually. In the cosmic web, in the space between galaxies, in the vast darkness that fills the universe, there is peace. Not the peace of consciousness, but the peace of simply being, of existing without awareness, without intention, without the burden of selfhood. This is the peace that matter knows, the peace of following physical law without choice or effort. It is a peace you can touch in sleep, in those deep unconscious hours when the self dissolves and there is only the body, breathing, metabolizing, maintaining itself without conscious oversight. Rest now in that peace. The journey is complete. The hidden universe has revealed itself, as much as it can, as much as words and imagination allow. What remains is silence and darkness, the natural state of most of the cosmos, the state to which all complexity eventually returns. This return is not to be feared. It is simply the way things are, the cycle of emergence and dissolution that characterizes all temporary forms. You emerged from unconsciousness at birth. You will return to it in sleep each night and ultimately in death. Between these boundaries, consciousness burns briefly, like a star in the cosmic darkness, illuminating a small region before fading, its light traveling outward to perhaps touch others before dimming into the universal darkness. But what light it was while it lasted, what wonder it enabled, what understanding it achieved. The very fact that you could contemplate intergalactic space, could understand something of its nature, could feel awe at its vastness, this is remarkable. This is consciousness fulfilling its highest purpose, to observe and wonder and understand. You have done this. You have completed the journey. Now rest, traveler. Rest in the darkness that contains you, that contains everything. That is the womb and the tomb, the beginning and the ending, the alpha and the omega of all that is. Sleep now. The universe continues without you needing to observe it. The galaxies spin. The space expands, the darkness persists, and in that darkness, in that vast cosmic night, countless stars burn, countless planets orbit, countless structures evolve and dissolve. Perhaps somewhere, other conscious beings contemplate their cosmos, asking their own questions, seeking their own understanding. Perhaps they too feel the pull of the darkness, the mystery of existence, the wonder of being conscious in an apparently unconscious universe. All of this is the one universe, the one cosmos, expressing itself in infinite variety while maintaining underlying unity. You are part of this expression, this cosmic exploration of possibility. Your brief consciousness is the universe waking to itself in one particular location, looking out through your eyes, thinking through your brain, feeling through your heart. And when you sleep, the universe does not sleep, but your particular window into it closes temporarily. Your individual perspective dissolving back into the collective flow of matter and energy and information that constitutes the cosmos. Rest now, dream now. Let the darkness take you gently into sleep, into unconsciousness, into the temporary dissolution that refreshes and renews. Tomorrow you will wake, consciousness returning, and the universe will still be there, still vast, still mysterious, still worthy of wonder. The hidden universe between galaxies will continue its slow evolution, patient beyond measure, persistent beyond time, dark beyond sight, yet full beyond imagining. And you will be part of it still, always, forever. Your atoms borrowed from the cosmos for a brief span before returning to the great circulation. The endless cycle of matter and energy that has no beginning and no end, that simply is, eternally present in the only moment that exists. The eternal now that is always here, always available, always the same, yet always different. Sleep now, cosmic child, cradled in the darkness, held by forces you cannot see, sustained by processes you need not understand. The universe takes care of its own, not through intentional care, but simply through the operation of its laws, the persistence of its structures, the flow of its evolution. You are safe in this cosmos, as safe as anything can be in an impermanent universe, as eternal as anything made of matter can be, given that your atoms will persist, even as the patterns they currently form dissolve and reform into other configurations. The journey ends in peace, in darkness, in the silence of sleep. The hidden universe between galaxies remains hidden yet known, dark yet illuminated by understanding, empty yet full of significance. And you, having contemplated it, having made this imaginative journey through the cosmic void, you now rest, complete, at peace, dissolving into the darkness that gave you birth and awaits your return. The darkness that is not nothing but everything, not ending but continuing, not death but transformation, not emptiness, but the fullness of potential from which all forms emerge and to which they all return. Rest, sleep, dream. The cosmos holds you. The darkness embraces you. The silence soothes you. And in this rest, this sleep, this darkness, there is peace, deep and complete and eternal. The peace that underlies all existence. The peace that is the ground of being. The peace that passeth understanding because it is prior to understanding, more fundamental than thought, more basic than consciousness itself. Good night, traveler. Good night, seeker. Good night, conscious fragment of the universe. The hidden universe between galaxies bids you rest. And in resting, you become one with it, one with the darkness, one with the vast cosmic peace that is and was and always will be.